Welcome to this webinar entitled Highlighting Organic Chemistry in Greece. My name is Adrian Minnaert. This webinar is part of a series organized by the Division of Organic Chemistry of the European Chemical Society, EuChemS. The previous webinar focused on Switzerland, and today we have Greece. I'd like to note that the lecture is recorded. The lectures are recorded and you can find them back later on YouTube. Just search for Highlighting Organic Chemistry and EuChemS and then you will find the lectures. At the start, I'd like to give the word to Professor Papadopoulos, the President of the Greek Chemical Society. Please take the floor.
Thank you so much. Good morning, everyone. Ladies and gentlemen, dear colleagues, dear friends, it is a great pleasure and honor to welcome you all to the event Highlights in Organic Chemistry in Greece. I would like to thank the Division of Organic Chemistry for organizing this important initiative and all of you for being here to support and celebrate this meeting. It is the chemistry that has a key part of science and of everyday life. It is the chemistry that helps us understand and improve health, energy, food, materials, and the environment. In Greece, as in many countries, we have excellent scientists working in many areas of organic chemistry in universities, research centers, industries, and schools. The aim of this event is to give visibility to this important work and to build connection amongst the chemists of different member societies, universities, and institutions. We believe that by coming together, sharing knowledge, and learning from each other, we can achieve even more, both in Greece and internationally. As the Association of Greek Chemists, we are proud to support excellence in both basic and applied organic chemistry. We are also committed to promoting the role of chemistry in building a more sustainable economy and society, one that respects people, the planet, and the future generations. Do I have the ability to share?
Yes. Yes, you're able to. Yeah, you should be able to share screens. Yeah.
Yep.
Okay. Here we are.
Yep. We see your slide, though not yet at full screen.
Yeah, I have noticed, but I think that it's okay now, is it? No.
No, on the other hand, I think if you enlarge it a bit, then we are able to see it anyway.
It's okay now, isn't it?
Yes, it is.
For me, it's okay. Okay. So, first of all, let me share with you a brief presentation of the Association of Greek Chemists, a brief one, and a few thoughts about the future of chemistry in Greece and not only. The Association of Greek Chemists is founded in 1924. It's converted to legal entity under public law in 1988. It has 10 regional departments, 7 scientific departments, and obviously it is a member of the International Union of Pure and Applied Chemistry and European Chemical Society. Otherwise, we won't be here. The Association of Greek Chemists is the official advisor of the state, the regulator of the chemical profession, which means you're not allowed to work as a chemist in Greece if you're not a member of the Association of Greek Chemists, which means the registration is mandatory. And one of its aims is to protect the science of chemistry, the profession of the chemist, and the interests of society. But where is a chemist employed today in Greece? Although 100% would prefer to work in the public sector, it's almost the opposite. Approximately 25% work in public sector, and the rest of the amount of 75% work in the private sector. More specifically, chemical industry, although the activities of chemical industry decreases in Greece. Pharmaceutical industry, cosmetics industry, environmental agencies and organizations, education, secondary or higher, research centers and institutes, food and beverage industry, hospitals and clinical laboratories, analytical laboratories and quality assurance, public sector and regulatory authorities. Also, a chemist can work as a freelancer, scientific consultant in safety and forensic chemistry. The unemployment rate of chemists in Greece. Oh,
Andrei and Nasos, I'm sorry, but
yes,
I think that we do not see your slides change. So I see the first slides only. Only the first slides.
Yeah, me
Am
too.
I right, Andrei?
Yeah,
Yes?
yeah, exactly.
I'm moving forward regular.
Yes,
Oh, yeah.
exactly. Just like this, yes.
Yeah.
Okay. Now you see this one?
Yes. Continue with this way.
And
yes.
now the next one? Or you still see the...
No, you have to click on the slide just to see the slides. Please.
Nothing? Still the first one?
Naso, it's not a presentation.
Yes.
That's why.
Has to be in the presentation.
Yeah, this is not a
Okay.
presentation.
Okay. This is, yes.
Maybe it's better to continue like that.
You were on slide number 6, is what I saw.
I'm
Yeah,
fine.
this works. Yeah, this
Okay.
works. This works fine. Yeah,
Yes.
please go ahead.
Okay. Now I'll try to go to presentation mode again. Hopefully. And what is...
As we can see your screen very well, it's maybe not necessary. If you just click on the next slide, that would work fine. Yeah.
Thank you.
Yeah.
Hopefully, the unemployment rate of chemists in Greece is very, very low. There are not actually any unemployed chemists, but the truth is that there are very, very few. The unemployment rate is really close to zero, but unfortunately, the earnings are far lower than their qualifications deserve. We can say that concerning the income, the profession of a chemist in Greece is underrated. Okay. And why is the unemployment rate so low? First of all, the reform of the higher education admission system with auctions by AGC in 2013 led to the appointment of more than 1,000 chemists in the secondary education. In addition, the exponential rise of investments in the domestic and not only pharmaceutical industry, the increased requirements in the field of accreditation, and the exponential rise of investments in the domestic production of cosmetic products. Let's see a few things about pharmaceutical and cosmetic industry, and we are getting closer and closer to the aims of this meeting. Unfortunately, there is no move, so we can see the full slide. The Greek pharmaceutical industry has increased its exports to many countries, primarily within European Union, but also to emerging markets, such as countries in the Middle East and Africa, with which Greece has strong economical bonds. Exports of pharmaceuticals from Greece are expected to continue their growth, which further strengthens the sector's turnover, which leads to more investments. The shift toward generic drugs has boosted the turnover of Greek pharmaceutical companies, as Greece has become a significant producer of generics within the EU and other international markets. According to the Hellenic Association of Cosmetic and Fragrance Manufacturers and Representatives, total cosmetic sales in Greece increased by 12.6% in 2023 compared to the previous year, reaching approximately 1.3 billion euros. The beauty and professional care industry continues its impressive growth, as in 2024, the global market is estimated to be around 700 billion euros, with an expected annual growth rate of 3.33% from 2024 to 2028. And what are the needs of pharmaceutical and cosmetic industry? Organic synthesis, here we are, chemical analysis, and regulatory. This way. And what about tomorrow? Near future. And this is a bad chemical joke. In the near future, the sectors presented, pharmaceutical and cosmetic industry, are those expected to have the highest demand. With the rapid development of the artificial intelligence, the future is expected to be at least interesting. With the increase of computational power, the role of a chemist will be differentiated. For example, we all know the uses of AlphaFold, and we must not, we must not forget that chemistry is a fundamental science and provides many opportunities for specialization. At this point, allow me to say that young chemists can bring new ideas, new energy, and new perspectives. They are the future of our science, and we have to help them grow, connect, and lead. Let this event be a celebration of science, but also of community. Let it inspire new collaborations, new goals, and new paths forward. And thank you very much for your attention, and I wish you a productive and inspiring meeting.
Thank you very much, Professor Papadopoulos. And then I give now the floor to Professor Yannis Likakis.
Yes, I would like also to thank Professor Nassos Papadopoulos, President of the Association of the Greek Chemists, and also the Organic Division of EuChemS that give us this opportunity for this great event. And today we have just 2 slides to share, okay? Just 2 slides. To share all these incredible presenters for this event. Just to add 2 numbers that in totally the organic chemistry laboratories are organized in chemistry departments, and the total number of chemistry departments in Greece are 6. The oldest one is the National and Kapodistrian University of Athens, and that was founded in 1980. Then Aristotle University Thessaloniki, the Department of Chemistry at the Aristotle University of Thessaloniki, and then follows University of Patra in 1966, if I remember right, and University of Ioannina in 1977. The University of Crete, the Department of Chemistry at the University of Crete in 1987, and the newest one, the Department of Chemistry in Democritus University of Thrace in Kavala. So in totally, per year, more or less 1,000 undergraduate students study chemistry in Greece, and more or less 1,700 undergraduate students studied chemical engineering school. Just a total number in Greece, just to have an idea. What about of chemistry department? And of course, included the organic chemistry division. So I'm glad to present you in a brief way the presenters today, and I'm going to start from Professor George Vasilikogiannakis, that is professor in the Department of Chemistry at the University of Crete, and his research interests focus on total synthesis and the biological active of natural products and analogs. The second one is Professor Christoforos Kokotos from the National and Kapodistrian University of Athens, Department of Chemistry, of course, and his research interests focus on green chemistry, organocatalysis, photocatalysis, and synthetic methodologies. Then we are going to see the presentation by Professor Vasiliki Sarli from our Department of Chemistry in Aristotle University of Thessaloniki, with his research interest focus on the synthesis of bioactive organic molecules and design the synthesis of natural product and biofunctional molecules. Associate Professor Gerasimos Rassias from the Department of Chemistry of University of Patra, and with research interest on organic synthesis and synthesis of drug substances and libraries of bioactive molecules in medicinal chemistry. Professor Alexandros Zographos from our department, Aristotle University of Thessaloniki, with research interests on divert total synthesis of natural product and development of novel reaction of targeted oriented synthesis, and of course, synthesis of chemical libraries. Professor Dimitris Georgiadis from the Department of Chemistry, National and Kapodistrian University of Thessaloniki, with research interests on design, synthesis of inhibitors and relative synthetic tools for the study of zinc proteases, and of course, selective synthesis of phosphonic peptides. And Associate Professor Konstantinos Neochoritis from the Department of Chemistry of University of Crete, with research interest on focusing on synthetic organic chemistry using the strategy of multi-component reaction. I would like to thank all these people that accept this invitation. And let's start with the first presenter, Professor Vasilikogiannakis. The floor is yours, please.
Thanks a lot, Yanni. Let me share my screen first. We're here. So, yes, let's go to the full screen mode.
George, just share your screen and then we can see the full.
Okay. Can you see the full now? I'm in full. It takes some time.
No.
Not really.
Not at the moment, no.
Okay. Can you see the presentation in general?
In general, yes.
Yes. But not in full screen, eh?
No, you have to share the screen, your screen, not the presentation, your screen.
Okay.
Δεν μπορώ να σου μιλήσω, τι είναι?
Williamson. It's a bug, Professor Vasilikogiannakis. You don't have to share the presentation. In order to have full screen presentation, you have to share your whole screen.
Yes, that's exactly.
That was my mistake.
That's exactly what.
Πρέπει να βγεις, Γιώργο, από το Zoom.
Γιώργο, the entire screen. The
Okay.
entire screen. Share your entire screen.
Okay. Okay. Entire screen. All right.
Yes.
Right. And now can you, I suppose you cannot, can you see it now? You don't. I just said, I suppose that I have done it correctly now, right, guys?
I think yes, yes.
Okay.
It is.
Let me see if I can go to my next slide. Of course I can go.
Also, that works. Also,
Yes.
that works.
Okay, very good. Thank you, Andriy, Pat, Yanis, Nasos, all the people who are involved in this organization. I can see we have a lot of participants today. And I think we will try to persuade you that organic chemistry in Greece is at its best, I think, historically. So I'm going to talk to you today about the development of sustainable photocatalytic transformations for organic synthesis. So of course, I don't need to say to this panel that we should move towards sustainable synthesis, which means a lot of things. We have introduced terms like pot economy, atom economy, step economy, redox economy, and to avoid all these labyrinths that we used to go through in organic synthesis today, and if possible, like Phil used to say, to achieve the ideal synthesis, everything in one step, one pot, one redox. We love singlet oxygen, as most of you know. A singlet oxygen, I think, is the definition of sustainable and green oxygen, because it gives the two oxygen atoms to the substrate that you want to photooxygenate and creates no waste. Singlet oxygen is a very good electrophile. It's the first electronically excited state of molecular oxygen. I suppose you can see my cursor moving it. And it's a very good electrophile simply because it has a completely empty homo orbital. In order to achieve this, we can transfer energy from very well-known photosensitizers, organic photosensitizers, or not organic. We prefer organic, of course, like rose bengal and methylene blue. So back in 2012, we discovered that if you take a simple furan, this is chemistry developed by the late and much missed Professor Foot at UCLA. You can photooxygenate simple furans that can come also from natural sources by degradation of sugars, and to make reactive intermediates like this in indione. But what we really discovered is we treat these 1,4-indiones in situ with a single primary amine via different ketalizations. You can end up suddenly with a compound which is this 4-pyrroline-2-on, which is a deconjugated lactam. Went back to the literature to find out that people claim that these kind of compounds are very, very sensitive, are very reactive, and it's impossible to isolate them. I can assure you that we can column these compounds in my lab. Of course, the main problem is that this bond that I show you here can move into conjugation with the carbonyl, of course, and then you don't have this compound anymore. But I'm telling you that we love reactive intermediates. Reactive intermediates are beautiful as long as you can tame their reactivity, because it's very high in energy, so you can do a lot of things. And one of the things that you can do with these deconjugated lactams is to treat them, for example, with an acid or an electrophile and generate an acyl-iminium cations. And when you generate these an acyl-iminium cations, you can trap them either intramolecularly from here, or intramolecularly by an external nucleophile. And we have developed also. You have to keep in mind this, plus keep in mind that something that most of you know, that the methylene blue is a photocatalyst that is blue in its cationic form. But of course, the methylene blue becomes inactive when you have an electron transfer process, which gives you the methylene blue radical, or an electron transfer, further electron transfer to give you the anion, and when it's protonated to give glucomethylene blue H, which is completely colorless. The only really active photocatalyst is the blue, the cationic form. Having this in mind, and as I presented to you in the previous slide, we used to use rose bengal to do this transformation, which takes this furan, and in one pot, it gives you this deconjugated 4-pyrroline-2-on. One day, that's a long story, we decided to change the photocatalyst, and what we observe, of course, when we use rose bengal, we get the deconjugated, but when one day we use the photocatalyst, we got a compound which is different, where the double bond is moving into conjugation with the carbonyl, but at the same time we have a change in the oxidation state next to the nitrogen. We have this gamma hydroxy gamma lactam of this type. So in order to understand what's going on, we have done a lot of mechanistic studies, and we isolated actually initially this compound with this, which is the deconjugated lactam. We treated it with methylene blue in dark. This is important, in dark. To make this compound for furans, we use singlet oxygen, as I told you before. But when you take this compound, you treat it with methylene blue in dark. Then you have a proton coupled electron transfer mechanism, which generates this very stable cathode radical next to the nitrogen, which is trapped, in this case, not by singlet oxygen, by molecular oxygen to give you this hydroperoxy radical, which of course can abstract the hydrogen atom and reduce in situ. We have different reducing agents in our solution to the corresponding hydroxy compound, which is actually the product that we receive when we do the reaction just simply by changing the methylene blue, the rose bengal to methylene blue. So we thought that we can use this chemistry in an intramolecular fashion. So if you have a furan in the alkyl side chain, you have somewhere at the gamma or the delta position an amino group, then it's possible to really synthesize indolidizins or pyrrolidizins of this type, where you have, in this case, the conjugated analogs with rose bengal, or if you use methylene blue, you can make indolidizin or pyrrolidizin scaffolds, the fully oxidized with the extra hydroxyl group in this case. Of course, why we want to make this compound? Because 30% of the natural alkaloids, you can see some examples here, but I will not go through the synthesis of some of these compounds. But I want to present to you today concepts. So to make indolidizins or pyrrolidizins, because 30% of the natural alkaloids, biologically active compounds, are either indolidizins or pyrrolidizins. So with the technology that we develop here, we can make them very easily. So then I always had in mind, my dream is one day to be able to do just synthetic chemistry by using light, only light, and playing a little bit with wavelength, with different photosensitizers. But the big problem is that when you use different photosensitizers, you have unproductive electron and energy transfer between the photosensitizers, which creates a lot of problems. It's really difficult to combine photosensitizers. We have developed one way to do it, which is the chemical switch. The idea is to have a photosensitizer to do one job, and then to have another photosensitizer to deactivate the first one without really do any isolation or columns or whatever, in situ to deactivate the first photosensitizer and allow a second photosensitizer to do a different job. And the idea here was to make fuse 5-6 member rings of this type, the type 4 and type 5 that you see here, by combining two different photochemical reactions. As I told you before, taking furan, for example, the rose bengal will end up with this 4-pyrroline 2-on, or using methylene blue will end up with a fully oxidized compound. And then the idea was to have an iodide and then do a second photochemical radical generation next to the carbon next to the iodide. So to generate a radical there, which can be involved in a 5x or 5-endo cyclization to get these kind of scaffolds that they do exist in erythrine alkaloids, in licorine, aspidosperma, etc. So, and the reaction works very, very well. Of course, this is not the one pot. We isolated the intermediates. We took them, we pushed them forward. Here, of course, in order to work, you need a stronger photocatalyst. In this case, we needed iridium type photocatalyst, the PC1 mentioned here. But we do like to do everything in one pot. The reaction works very, very well with a variety of substrates. We can make 5-6 member fused rings, but you can make also 5-5 that they do exist also a lot in nature. The interesting thing is the following. Okay, we thought that maybe one solution to do the two photocatalytic reactions using just the iridium photocatalyst from the beginning. And very low, as you see, percent, the 0.03% is enough for the energy transfer and the generation of singlet oxygen. And then you dump a little bit of the iridium catalyst, a little bit more, 0.08, and you generate the radical here next to the iodide, which cyclizes and give you the final product in one pot. But what if you want to make this compound the fully oxidized with the OOH here? Then you are obliged to use methylene blue to end up with this intermediate, and then move forward with this intermediate using the iridium catalyst in this case. So you should change photocatalyst in order to create this type of scaffolds. And the idea was to actually, in order to do it in one pot, to deactivate methylene blue. It's very well known that under photochemical conditions, the methylene blue, in the presence of the pair that is used in the second step to generate the radical here that I told you, the dipair under photocatalytic conditions with light can really do a 2-electron transfer to methylene blue to generate a leucomethylene blue H, which is, as I told you, completely inactive. It's not a photocatalyst anymore. So we thought that if we irradiate our solution, which contains the pair now, eventually we will see the photo-bleaching, we'll lose the blue color, and in the presence of the iridium, it's very, very possible that the second reaction will start. It's a beautiful phenomenon. You see here, when we started, for example, with 1% methylene blue, which is not necessary, but in purpose we use extra methylene blue or even extra 5% or 8%. Look at this. With 1% methylene blue, after the first step, we needed to irradiate for 10 more minutes, in order, nothing happens in 10 minutes, but just the transformation of the catalyst methylene blue to leucomethylene blue H, suddenly you lose the color of the blue color of the methylene blue, and suddenly iridium starts to work, and the reaction happens in 1.5 hours. If in purpose we use more methylene blue, this is a control experiment, then the deactivation of the methylene blue, which is more, takes 45 minutes, and then after 45 minutes, after all methylene blue is deactivated, you see the second photocatalyst starts to work. And if in purpose we use 8% methylene blue, then it takes 9 hours for the deactivation, 9 hours of the irradiation, and then it starts to work. Of course, we know what's going on exactly. You deactivate the one photocatalyst in order to allow the second one to do another different job. And that's the idea, actually. I hope we'll find more switches in the future. But just to prove to you the beauty of this chemistry and how easy makes our life is, we synthesize via iode of urine in 2 synthetic steps, for example. And then with methylene blue and iridium photocatalyst in situ in one pot, you generate something like this. When the DR is this electron-rich aromatic here, and you do a Pictet-Spengler cyclization. In the last step, we just dump a little bit of formic acid in situ, you generate aristotramidine. The same concept, you generate erythrotridienone, which are compounds that have been synthesized in the past in 20 synthetic steps. I think this is a really good simplification, and it is sustainable. So then we thought that we got a funding from making compounds that are actually two pyridones, and two pyridones are everywhere around the cancer and the tumor, anti whatever. So people, the pharmaceutical industries, they are very interesting about making two pyridones, and we thought that we can expand our idea of starting from furans and making this from the hydroxy compound. If you dehydrate them, the hydroxy that I showed you before in situ, to generate this exocyclic double bond here in compound 4. And then if you treat it with, for example, NAS in methanol, you will get an iodo group here where you can generate this radical that is possible to engage with this double bond to generate a radical here, which goes back, opens up the 3-member ring, you generate a radical stable next to the nitrogen, which loses a hydrogen atom, and it gives you the two pyridones that we want to synthesize for a lot of pharmaceutical purposes. The idea works, I will not go through this optimization, of course, the idea works like a dream, and we managed to avoid this fully reduced compound, and we got exclusively compound 6A, which is exactly the compound that we want, starting from these kind of compounds. Reaction works with a variety of substrates, but again, the important thing for me is the chemical switch that I told you before. We take a simple furan. This is one pot process. We don't isolate anything. You take this simple furan, you treat it with methylene blue. You get this hydroxy compound. you dump a little bit of formic acid, you generate the double bond here, you just add in the same flask some NAS in methanol, you generate this compound, and then with the methylene blue still in present, you do the switch. You use another photocatalyst, which is in this case is beautiful because eosine Y can do the work. We don't like metal-based photocatalysts. In this case, we have only organic photocatalyst, methylene blue. The eosine can generate the radical here. And it can, the pathway that I described to you before starts to get the pyridone. One synthetic operation, we don't isolate anything. The reaction works even, it's more beautiful, the protocol, when we have the internal nucleophiles to do the job. We have, for example, somewhere in the static you run an alcohol or a nitrogen. And in this case, when you use an AS, actually, the nucleophile is not methanol and is not external, but internal, which gives you the option to make lots of scaffolds that exist in nature. Can be also intramolecular using indole in this case. It's another type of compounds, very interesting compounds. So the nucleophile that I told you in an AS step is not only methanol, it can be a lot of different things. So, and the reaction is very interesting because we tested this reaction and we found out that the next to the iodide, the presence of two electron-rich atoms, two atoms like nitrogen or oxygen, actually accelerates, give the reaction. And when we have iodides in different positions, only the alpha position is actually the position which is close to the oxygen and nitrogen that works very well, which means that there is something special with this substrate. When we made this substrate, for example, with one oxygen here, this iodide is removed selectively and not the other one, which is not activated. There is a type of activation. The mechanism is the mechanism that I described to you before. There is a type of activation to the iodides that bear in the alpha position, either an oxygen or a nitrogen atom or both. So we thought that we can extend this idea into from the very narrow scope that we had before to make it more general, and in general to have two heteroatoms in this position. The X can be oxygen or nitrogen, and to actually make polycyclic OO or NO acetals in this case. So we started from very simple vinyl ethers, for example, with an AS and in the presence of an allylic or homoallylic alcohol, you can generate compounds like this where the iodide is activated next to in the next position, it has two oxygen atoms. It works very, very beautiful. And this way we can make all these cyclic OO and later, as you can see here, if you have nitrogen, NO acetals. And again, the chemical switch works very, very well. This is an interesting piece of work because actually, if you go to this ChemCom paper, you can see that we found out that the pair in this case have 5 different rules to play in this actual transformation. So finally, we thought that colibactin is the holy grail today in cancer therapy. The colibactin has been proposed to have this structure, but we don't know really. We don't know. We don't have an NMR. They know by MS. They assume that this is the structure actually. And it's something as cytotoxic, which was isolated from E. coli bacteria and could induce double-strand DNA breaks, which leads to cell death of different human cell lines, and it's related with cancer. Lots of studies have been done, and we thought that there is a resemblance between this, what we call colibactin warhead, actually, with the compounds that we synthesize in the lab. And we thought that maybe we can do the first photocatalytic cyclopropanation. That's the idea here, using actually diiodomethane, which is a technology that has been developed actually by Marcus Suero, but using, of course, metal-based catalysts. Can we use eosine, for example, to take a compound like this that you have seen it a lot, the compound of number 2 in my presentation, and do cyclopropanation without carbines, just photocatalytically using diiodomethane, but with organic photocatalysts? this is the substrate that we made. So what is the idea really behind it? Our idea was that if we start from a compound of type 2 with exocyclic double bond, of course, eosine will be in the excited state. Eosine, we have an electron transfer with d pair. We make the radical cation of d pair, which can, the radical cation can react with another molecule of d pair to generate the cation of d pair, and at the same time, the alpha amino alkyl radical of d pair, which radical, because of the beautiful work of Daniele Leonori, we know that these radicals are really can do nice things. And one of them we assumed was to be, if we use a diiodomethane here to take an iodide atom to generate this radical here, which can engage with the double bond, the exocyclic double bond of compound 2 to generate another radical here next to the nitrogen, very stable, which can lose another iodide atom to generate the cyclopropyl ring in this position. It does work beautifully, and it does work in the presence of other iodides, in the presence of sensitive groups, and it does work very, very well. And we have the first cyclopropanation with just using eosine Y as photocatalyst, an organic photocatalyst, not metal-based photocatalyst. But we have another first one here because this chemistry was known with metal photocatalysts by using diiodomethane, and never people have used also, in this case, we use the bromoacetate of this type, the bromoacetate, and the reaction works really well, which gives us an extra handle here, the ester group, for further functionalization, very important for organic synthesis. So the reaction works very well also with this one. But again, the important thing for us is that we can do everything in one pot, taking the furan, treating it with methylene blue in situ in order to get the dehydration of the alcohol, to get the double bond, a little bit of the formic acid, and then without really isolating anything, change the photocatalyst to eosine Y, diiodomethane or bromoacetate, the chemical suites idea, because we use the pair also to deactivate the methylene blue. In one pot from this furan, you make this type of scaffolds. We like it a lot. So I'm not going to talk to you today because of the time restrictions for the 2+2 photocatalytic reactions that we have done. I will just tell you that because we do lots of singlet oxygen chemistry, and we have generated a lot of oxygen polycycles that they do exist in nature, or nitrogen-based polycycles, alkaloids that they do exist in nature during the last 10, 20 years. In my lab, we thought that always we can really optimize and scale up the singlet oxygen reactions, and we have developed something which is, the idea was to do the photooxygenations in nebula, in clouds actually, and we take the solution that we want to photooxygenate with a photosensitizer and the substrate inside. We nebulize it with the pneumatic nebulizer that the MS analytical chemists use for MS purposes. And we nebulize this solution in a, this is actually in the prototype here, it was just simply a column chromatograph in the lab. Now we go into more automation of the system, which is surrounded by LED tape lights, those lights that we use to decorate our house in Christmas. And it works really beautifully, and we can go with productivities. Of course, we don't have the problem of the light attenuation here, Beer-Lambert law, and all these kind of problems. We can really scale up it very, very fast without having hydroperoxides or peroxides in kilos and things, because we immediately reduce everything here in with dimethyl sulfide. And we go up to productivities like, for example, here, 1.43 millimole per minute, which means that if you operate the system for a few hours, or you can make kilos of the compounds that you want to produce. And this is something also important in modern organic synthesis. And we have used the system in more complicated situations, and it works very, very well. This is actually the first, it's not like this anymore, but this is the first prototype that we synthesized in the lab. I hope that I persuaded you that we have developed multi-photocatalyst photocascades, which provides alkaloids motifs starting from readily accessible furans, photocatalytic synthesis of OO and NO acetals. The developed methods were devoid of complex factorial group manipulations and protections. I suppose you didn't see a single protecting group in my presentation. I talked to you about the colibactin, not so much, and the nebulizer. And I want to thank all these people who have done this job, but especially the most two very, very amazing postdoc, Dimitri Kalaizes and Tamsi Montagnon, and of course from the recent project that I presented, Yanis Zahilas, so many other talented chemists in my lab that I was very, very blessed to have them. And thank you very much for your attention.
Thank you very much, Georgios, for a really inspiring lecture. And we go now to the Q&A session. So for the participants, they can put their questions in the Q&A box. For the panelists or the speakers, they can also raise their hand, so to speak, in the raise hand button at the bottom of the screen. In view of the time, I will allow a few questions because we are running a bit behind schedule, but I would like to allow a few questions. Please go ahead.
You see, Pat, I was very convincing. Everybody understood
You were
everything.
super
Or maybe
convincing.
the Greek chemists know my chemistry, I think.
I suppose they do, and not only in Greece, Georgios, but
in order to make fun of Professor
Alexandros has a question there.
Our president Nasos, as you can see, you said not IR. We follow it, not IR. Everything is visible here, light. Okay?
That's good that you really enlightened the chemistry. One question I had, Georgios, is that how do you balance all these different sensitizers? So do you look purely at the redox potential that is given, or do you also determine redox potential yourself? Because that has to be balanced, right? If you add more than one photocatalyst in the reaction.
Exactly. Andre, this is a really beautiful question. I can talk for hours, but of course
that's not the point.
You cannot balance everything. You have to very carefully look at the reduction potentials of the catalysts that you use. Very, very important. And at the moment, this chemical switch idea is actually just one example that I showed to you. We haven't done much with other photocatalysts. It works in this particular case, but I know all these limitations. But I hope that in the future we'll be able to find different type of switches, playing with. Of course, there are some known playing with pH or playing with some other factors, but again, the field is still really primitive at the moment. Of course, reduction potential is a very, very important factor. I know exactly what you mean. Thank you.
Thank you. And I see that Alexandros has a question. Please, you can just unmute and pose your question.
Thank you so much, George. Excellent talk, like always. So let me have a quick one. You have an exocyclic double bond in this case. You have the slide in front of us. So this exocyclic double bond, let's say that you want to quench it not with methanol, but instead, let's say, with a sulfide. Is it going to work in order to expand the 5-member ring or no?
I suppose that is feasible, of course. I suppose that is feasible. We haven't tried it, but
unfortunately, because
reasonably, it's a very good nucleophile sulfide.
We had the experience to try this, and what we saw is just a reduction of the double bond, not expansion. So this is quite interesting, and I thought you might know something.
Okay, so just the reduction of the double bond, right?
Yeah.
All right. I'll keep it in mind. If we sort it out, maybe we can collaborate in what you want to do.
Okay, thank you.
Thanks a lot.
Okay, thank you. And with that, I suggest we swiftly go to the next speaker, and that's Professor Kokotos. Please go ahead. Also, then you have unshare, Georgios, so that Christophoros can share his screen.
I'm I stop sharing. Is it okay? Yeah.
Yes, it is okay, and I see already the presentation of Christophoros appearing, though not yet in full screen.
Do you see my screen?
I do see, but we don't see it in full screen.
Now it's in on full screen, isn't it?
Oh, wait, it takes a bit of time, I think. Nope. Yeah,
I had the same problem, Christophoros. I think I had the same problem, and and the solution was to share
the full screen. Yeah. Okay.
correct.
Right,
What
right.
about now?
Yes,
Yes,
this
yes,
is much
yes.
better.
Okay.
So please go ahead. You have thumbs up. Yeah.
Yeah, the problem I have is doesn't let me do it again because it doesn't move the slides.
Ah.
Okay. So let me share the screen now. Yes. And now it should work, and also the slide is moving.
Correct.
Yeah, perfect. Okay,
Yes,
thank
perfect.
you. Thanks. Okay, so good morning, everyone. It's a great pleasure to be here. I would like to start by thanking Yanis and Nasos for the kind invitation and the nice event, and obviously Andrew and the Division of Organic Chemistry of EuChemS for this series of events that are going on for a couple of years with Pat Giri initiating that. So thank you. And I would like to talk to you about some of the research, like an overview or a highlight, if you wish, of what we're doing in Athens the last 11 years that I have started my independent career. So just a slide regarding our university. As Yannis said, is the oldest university in Greece, situated in Athens, which is the capital of Greece, that has more or less half the population of the country. It is considered to be the oldest university in the Eastern Mediterranean and the Balkan Peninsula, having more or less of 100,000 students and around 2,000 faculty members. As correctly stated by Yanis, our department, the Department of Chemistry, was established in 1918. It has more or less 150 undergraduates and 150 postgraduate students per year. Faculty members are around 46, and we have 8 laboratories, including the Laboratory of Organic Chemistry. For you, probably the most famous organic chemist that has ever been in our department was Leonidas Zervas, who is the guy who introduced the CBZ protecting group in amino groups and amino acids and peptides. So our work focuses a lot on the idea that came out in an editorial in Nature a couple of years ago, that we need to change the way we teach chemistry if we want our planet to survive. And in order to do so, we need to follow some guidelines. For us are these Sustainable Development Goals of UN. And if we do that, we're gonna avoid to see photos like the ones you can see at the bottom of the slide. So I was quite fortunate when I was in my earlier research years that I was mentored by people like Varinder and Sir David Macmillan, and using these new emerging green technologies that are your weapons to do sustainable chemistry. And I was quite fortunate to see some of them, like electrochemistry, organocatalysis, photochemistry, and continuous flow. So when I started my independent career, we started working in organocatalysis, which is the use of small organic molecules as potential catalysts, a field that was reborn in the year 2000, and a couple of years ago, a Nobel Prize was awarded in this. So when you begin, you go to the inventory of the laboratory, you see what you have in bulk, and you try to do chemistry with that. And thanks to Leonidas Zervas, we had a lot of amino acids, and we decided to build organic molecules that can be employed as chiral organocatalysts for virus reactions. However, as the years went by, we decided to move forward to oxidations, because these are quite useful reactions. And since George in Crete was working with oxygen, we decided to do something different, and we decided to work with hydrogen peroxide. Hydrogen peroxide is an environmental friendly oxidant. Its only byproduct after oxidation is in principle water. It's an aqueous solution that you can use, but it has a huge disadvantage. It's quite poor as an oxidant, so you have to activate it before use it. And usually in literature to do so, you have to use metal complexes. So all advantages you have with hydrogen peroxide as green concept, you lose them because of your catalyst. So our idea was to use small organic molecules to activate hydrogen peroxide. And if you go back to your undergraduate studies, you see this key fundamental equilibrium where you have the addition of water to a keto group for the hydride. So if you strategically plan activating groups like perfluoroalkyl groups on the carbonyl group, you can shift this equilibrium towards the diol form. And maybe our idea was that we could activate hydrogen peroxide to perform oxidations. Our proof of concept was used in this oxidation of silanes to the corresponding silanols, and the commercially available compound, this trifluoromethylacetonophenone, was found to be a really good catalyst if you couple it with acetonitrile, terbutanol, and the NECUS buffer of 11. All of these are extremely important for the reaction outcome, and you can perform this oxidation quite nicely. Key contributions during our years of research was the oxidation of anilines that help us understand the reaction mechanism, and obviously the epoxidation reaction, the oxidation of double bonds. So throughout the years, we have used this methodology to oxidize different things like heteroatoms followed by other reactivities, or if you can strategically put a nucleophile at the appropriate position close enough to the double bond, after the epoxidation, you have a cyclization event occurring leading to all these structures. One thing we couldn't do, and we still cannot do, was the asymmetric version of this reaction. So after numerous attempts that all of them failed, we decided to couple our strengths with the group of Christoph Spar in Switzerland and use his chemistry on atropoisomeric compounds in order to do chiral catalysis. So a really talented student of mine, a PhD student back then, Iro Triantafyllidi, went there to try to solve this problem. We failed to do the enantioselective version, but what she recognized was that this atropoisomeric aldehyde could be used as a catalyst to activate hydrogen peroxide to perform oxidations. And this was the first example in literature that an aldehyde is used in substoichiometric amounts to activate hydrogen peroxide. We also studied the reaction mechanism. It's quite complicated, and due to restriction of time, I'm not going through it. So the main part of the talk will be about photochemistry and photocatalysis, which is what we are doing the last 10 years or so, and most of the people in the group are working on this. This is the concept of using light, and after George, it's quite easy to see that it's quite easy. This is not a reaction, this is not an area that is quite new. In 1912, Giacomo Schiamonzian of the University of Bologna in Italy decided to put some reactions at the rooftop of the department during the summer and actually proved the idea that photochemistry can be used in organic synthesis. But then for almost 100 years or so, the field, I would say, was a little bit dormant until three groups, Nisevich and Macmillan, the group of Yoon and Stephenson, decided to use rubipi, metal-based photocatalyst, in organic synthesis. Nowadays that we have in our hands some mild irradiation sources that solves a lot of the problems in the past. And also we know a little bit better radical reactivity, something that was, I would say, dodgy in the past, but nowadays there are clear ideas on what's going on in them. We are more confident to do photochemistry. So we decided to couple photochemistry with organocatalysis in a field that we could call photoorganocatalysis, which would be the use of small organic molecules to promote photochemical reactions. So going in 2020 and a little bit later in time, we have found that phenylglyoxylic acid, which is a commercially available compound, can promote photochemical reactions, like, for example, this hydroacylation reaction between an aldehyde and an activated double bond to form ketones. The nice in of this reaction is that you use only 20 more % of your promoter. You can use water as a solvent, and CFL lamps, extremely cheap household lamps that you can buy from your local supermarket, are the irradiation source of this protocol. This one works quite well. Throughout the years, we have more than 70 substrates that work equally well. The reactions yield vary between 30 to 70% in most cases, if not all. The only class of compounds that doesn't work in our hands are styrene compounds, and this is the only limitation of this protocol that we know. What about the reaction mechanism? Phenyloxylic acid is actually not a photocatalyst, it's just a photoinitiator. Depending on the irradiation source and the solvent you use, here we have used water, the photodecomposition of the molecule changes, and in water, you can go to benzaldehyde via this benzoyl radical. You can take advantage of this benzoyl radical to initiate a process with the aldehyde leading to acyl intermediate 1, which reacts with a double bond leading to radical intermediate 2. Then via an open chain propagation with another molecule of the aldehyde, you have your final product. Although what our mechanistic studies have shown back then was that water, which is supposed to be the solvent, was not so innocent in this process, since a very, very small amount can participate in the reaction mechanism as well. What is really nice in this field that we're working on is that you can work with extremely talented people. And I had the pleasure throughout the years to work with some of them, like Dr. Irotria Dafilidi and Dr. Petros Gizis, who is actually now an assistant professor in the Laboratory of Organic Chemistry in the Department of Chemistry of the Aristotle University of Thessaloniki. And when you work with these talented people, you can do different things, discuss chemistry, and see different things. So as Yorgos said earlier, we can use oxygen from air to perform oxidations. This is actually the greenest way to do oxidations. And we decided to couple photochemistry with aerobic oxidations to perform one of the simplest reactions, in my opinion, the oxidation of sulfides to sulfoxides. Why this reaction is so important? But because you can make molecules like modafinil or sulforaphane, which are extremely important compounds. Some of them are really useful APIs. And initially, we have done that with anthraquinone, although nowadays we can do it with various catalysts. If you have plenty of time and you want to make fun, you can also exchange the organic solvent with some alcoholic beverages like rum and tequila, and the reaction works equally well in some cases, as we have seen earlier this year. But what I would like to finish off with my talk is something that we're doing the last couple of years or so, and started during COVID, and it's about recycling of plastic waste. I'm sure we all agree that from 1950, when plastics came to life, have improved our everyday life. However, plastic waste is a real problem, and in 2019, around 400 million metric tons of plastic waste were produced, with a projection to be double in the next 20 years. And a fact that is quite problematic is that by 2030, there is a projection that the amount of plastic waste in oceans and seas will be more in weight than the actual living organisms in these environments. So we have to do something about it. What we do currently, we usually use landfills, and we actually burn plastic waste. This is quite problematic since we produce greenhouse gases. And also, we also help the microplastic problem, which is currently a big issue throughout the world. The other solution is the recycling process, where we use the plastic waste to use them again. This is usually leads to downgraded materials, and a big problem is that only 7 to 8% of plastic waste are being recycled. But even after recycling, these downgraded products are usually ending up as waste. So we don't solve the problem. So what we can do is use upcycling, which is the conversion of plastic waste to high added value chemicals. And one way to do that is using photochemistry. So we decided to go with a simple solution with polystyrene, that we can use our anthraquinone aerobic photochemical condition to break it down to benzoic acid, which is a known food additive. If you're not convinced that this is something useful, you can also see that in just 2 steps, we can convert benzoic acid to aspirin. So our idea was to take plastic waste based on polystyrene and convert it to medicine. So your starting material are quite obvious plastic waste that you can use every day. You can see the yields that vary quite well. And after we did that initial heat with athraquinone via a direct heat process, we also found out that we can use indirect ways to perform the same reaction using thioxanthone-based compounds with a hot reagent like bromoacetonitrile or NBS. And in these both cases, the yields are higher. The substrate scope is also quite larger, as you can see. And we also tried for the first time a large-scale approach, about 20 grams of plastic waste. As you can see from the photos, we need 4 Kesi lamps to do the reaction and 2 weeks of reaction time. I would say this is not optimum, obviously, but it's just a proof of concept. And you can also do the recycling of the process, as you can see, although after 2 or 3 cycles, the yield is decreasing significantly, but you can actually improve it a little bit if you add in each cycle some additional amount of NBS. So as I told you before, a solution to the large-scale synthesis, if we want to avoid this amount of time, is a continuous flow processes. And we had actually applied for a number of grants to do so and get an equipment to do that, but we failed to acquire the funding. So we decided to build in our own. And at this point, I would like significantly to thank Professor Polisos from the University of Melbourne in Australia, Professor Tim Noel from Amsterdam, and Professor Marcus Baumann from Dublin, that actually helped us a lot in acquiring the appropriate things in order to make it happen. And you can see our house building continuous flow apparatus that we have built and tried to work on. This is quite nice because, as I told you before, if you have extremely talented people like Dr. Vera Dermedzidou, Dr. Olga Mudanea, and PhD students like Naya Stini and Stamatis Serviu, you can build this apparatus and they immediately go trying on in a reaction that we really know really well, this hydroalkylation reaction between an aldehyde and a diad to get to drugs like moclobemid. So this is a work in progress that hopefully in the near future, we will have some nice results on the upcycling of plastics in flow as well. So by that, I would like to go to the most important slide of all, which is the one with the acknowledgements. I'm blessed throughout the years to work with quite talented people, like the ones you have seen in the slides, or you can see over here. As well as in other people that also contributed in the past in our work. I'm also really in depth around funding from ELIDEC, Greece, and Europe that make everything happen. And obviously, I would like to thank all of you for your kind attention. Thank you so much.
Thank you, Christophoros. Well done. Very, very interesting lecture indeed on a variety of topics. Who has questions? So for the participants, please use the Q&A button, Q&A box. Or the panelist can just use the raise hand button. Maybe I can start with a question of my own. So in the activation of hydrogen peroxide, I can imagine that is a difficult reaction to control. Do you have measures to follow spectroscopically the hydrogen peroxide, or how does that work?
You mean on different oxidation levels, or
right, or hydrogen peroxide consumption?
Yeah. So in most cases, we don't have multiple oxidations going on. We have one example with the sulfides. So depending on when you use sulfides, depending on the conditions you use, you can go either to sulfoxide or sulfone.
So yeah.
There are different ways you can control that. For example, if you don't have acetonitrile in there, then you stop the pain pathway, which is involved in aqueous acquisition. So acetonitrile reacts with hydrogen peroxide, leading to peroxycarboxymic acid. This is quite an active oxidant to perform the second oxidation. So if you avoid the use of acetonitrile in the solvent solution and you reduce your reaction time to just 1 hour, you can stop the reaction to sulfoxides. However, when you add acetonitrile there, you have a different pathway and you go to sulfone. This is something we are actually now also verifying. In most of our reactions, we follow the reaction with direct infusion high resolution mass spectroscopy. So our early assumption that we're trying to wrap it up right now is that in the first step, you actually have a perhydride from the diol that performs the first oxidation. And the second step, peroxycarboxymic acid kicks in and helps you for the second oxidation step as well. So you can follow the reaction by direct infusion high resolution MS. You can use different spectroscopic techniques as well, but we haven't done it.
Thank you. And it's an intriguing remark that you make, that with hydrogen peroxide and acetonitrile, because I see in spectroscopy or in oxidation catalysis often this combination used. I'm not sure whether everyone realizes that hydrogen peroxide can actually add to acetonitrile to form a peracid.
This is a wonderful work from Payne from 1961. It's a GOC paper. It's a very, very interesting paper. And if you want to improve the efficiency of the process, you usually use trichloroacetonitrile.
Okay. Take home message. Okay, I see no questions in the Q&A box and no raise hand. And thanks once again. And in view of the time, we go to the next speaker, Vasiliki Sadli from Thessaloniki. Please, the floor is yours.
Can you see my presentation?
We do. Not yet in full screen though. Yeah, but we do now. Look, we got trained over the day in doing this. Can you also change slides? Does that also work?
Yes.
Yeah, even that works. Okay, go ahead.
Okay. Okay. Thank you for the kind invitation. I have to thank first Ioannis Likakis and the European Chemical Society for this event. It's my pleasure to be with you here today. I will present you some of our results on the development of 2-amino adenine-based proteolysis targeting chimeras. As we know, FDA has approved drugs from approximately 400 human proteins, while there are 3,000 more that are associated with disease, but have not been targeted yet. So we have this new targeting protein degradation approach that it refers to the use of small molecules to degrade proteins. Actually, these molecules interfere with the intracellular balance between the newly synthesized proteins and the damaged or misfolded proteins. Here you can see a general structure of a PROTAC, the proteolysis targeting chimera. It consists of two parts. The first part recognizes a protein of interest, and the other part binds to an E3 ligase. Now, our PROTAC is a catalyst. When it recognizes the protein, then a tertiary complex is formed, and ubiquitin is transferred from the E3 ligase to a protein, and then upon polyubiquitination, the protein goes to proteasome and it is degraded. So when we develop a PROTAC, we know a warhead, we choose a binder for our protein of interest, we know the anchor that recognizes A3 ligase. This that we don't know is the length, the shape, and the nature of the linker that is suitable for the formation of the tertiary complex. Now, what are the challenges for product synthesis? Usually we use a trial and error approach. This means that it's a laborious process. We have to synthesize many products using different linkers. Of course, there is a difficulty in choosing the proper linker attachment point without losing the affinity towards our proteins. Some of the ligands that are used, such as pomalidomide, are sensitive to acid-base oxidation and hydrolysis. And we have to consider also other things like that the products are large molecules, they have many functional groups, and this might create synthetic problems. And also we have to consider the stereochemistry because many, quite often, chiral centers are involved. Usually for the coupling of warheads to anchors, we use the formation of an amide bond, and these reactions may suffer from low yields, though click chemistry, solid phase synthesis, and late stage synthesis via ruthenium catalyzed stage amidation has been applied, but they don't find these methods wide applicability. Now, products, as I said, are large molecules, and they are tricky to be purified. They are accompanied with similar impurities, so at the end you have to purify your compounds with HPLC. Furthermore, the NMRs can be really complicated, as you can see, and quite often when flexible linkers are used, we have the formation of rodamers. Now, going back to our subject that I will present you today, we aim to target our mitotic kinases, aurora kinases, and TTK. Why? Because these kinases are important mitosis, controlling mitotic progression and proper chromosome segregation. Also, these kinases have been linked to various cancers and are overexpressed there. For example, Aurora B is considered a very good cancer target. It's overexpressed in various malignancies such as bladder cancer, ovarian cancer, breast, etc. Today, there are several inhibitors of these kinases in clinical trials, phase 1, phase 2, and during the course of our work, 3 products have also been reported. So it's a very active field. Now, why to synthesize products? There are several advantages to target proteins using products, because they may target undruggable proteins. They may not bind to the active site. They can degrade the protein, so you can avoid drug resistance, and you can use low doses because products have a catalytic mode of action. Now, the challenges are many. Of course, there might be some synthetic problems. They are large molecules. This means that they may not penetrate the cell membrane, and they may have bad solubility and quite often off-target toxicity. For our project, we choose an ATP binder. We targeted our kinase and TTK. We use various linkers, and we coupled this to a cereblon ligand, pomalidomide, and to a VHL1 ligand. This binds to von Hippel-Lindau ligase. As a warhead, we chose reversing. You can see here the crystal structure of TTK and Aurora kinase B with reversing. And here you can see that this is the morpholin ring that extends. It is solvent exposed, so this is considered a nice point for linker attachment. So we changed the oxygen to nitrogen. We synthesized azareversin. We knew from literature that reversin inhibits Aurora A with an IC50 of 876 nanomolar, Aurora B with approximately 99 nanomolar, and TTK with 6 nanomolar. So we also found another inhibitor, MPS1, which was selective. It is reported to be a selective TTK inhibitor that inhibits TTK with an IC50 of 50 nanomolar. We also aimed to choose several structural features, and we aimed to synthesize SF1 and SF2, two new molecules that could give selectivity to our products. We started our synthesis with dichloropurin, and first we protected the dichloropurin, and then with an nucleophilic aromatic substitution, we could obtain the isopropyl thiophenylaniline derivative, and then with oxidation and following by Hartwig-Buchwald reaction using palladium acetate cesium carbonate, we could isolate derivative 678, which after the protection gave our inhibitors in good yields. For this reaction, we also used the palladium TPA potassium carbonate XPhos system, but here the reaction didn't work. Neither the nucleophilic aromatic substitution using the piperidinol tube. Now, for the synthesis of pomalidomide derivatives, we needed large quantities of pomalidomide. So we started from L-glutamine, and then first we bocylated, and we performed one pod cyclization of protected glutamine to the glutarimide CSI 102. Using paranitrophenyl chloroformate and triethylamine and DMAP. We managed to perform this step in 70 to 75% yield. So we moved to the synthesis of pomalidomide. This is a known procedure. 3-aminoglutamine reacted with 6-nitrophthalic anhydride, and after reduction, we could obtain pomalidomide. Also, we synthesized the fluorothalidomide, and because we needed the methylated compounds, we also methylated the amino group because we needed these methylated compounds for mechanistic studies. And now our target was to change the length and the structure of the linkers. And we use different linkers with different carbon atoms from 3 to 13 atoms. We use linear linkers, etheric or heterocycles, and for the coupling of the different building blocks, we use amide, the formation of an amide bond. In total, we synthesized 6 VHL-bearing chimeras and 20 pomalidomide-bearing chimeras. And so we started from our compounds, and we added the succinic anhydride and all bulk glycine. It went at a carboxylic group or an amino group. Now, for the synthesis of pomalidomide derivatives, in general, I have to tell you that this amino group has low nucleophilicity. These reactions, the alkylation of pomalidomide with anhydrides and chlorides, in generally gives access to these intermediates that we want, but the yields are often low. The reactions of amines with fluorothalidomide are better, and they give here better yield, 60 to 90%. But also here, for example, if we use a PEG linker, the reaction was low, 28%. Having in hand the different building blocks, we continued to the formation of the amide bond using DCI and HOBT. So we're able to synthesize our chimeras. And here you can see products having a linear, pegylated, or other heterocycles as linkers. We had a variety of structures. And also we moved to the synthesis of VHL intermediates, starting from para-bromobenzylamine. We calculated a Heck reaction to form the 4-methylthiazole, and we coupled 4 with the hydroxyproline derivative 9. And after with HA2-DPA, and after the protection, we could synthesize the VHL ligand. We had to synthesize also the 4S epimer, starting from 2S 4S hydroxyproline, and this was obtained by inversion of the configuration of the hydroxyl group of 2S 4 hydroxyproline. We needed these derivatives because they don't bind to the E3 ligase, so it's good for, as I said before, for mechanistic studies. After that, having in hand VHL, we could add again different functionalities with glutaric anhydride, succinic anhydride, and PEG groups. We managed to prepare linkers to enter at carboxylic group or amino groups. And again, we synthesized various VHL bearing degraders. We had to study the stability of our compounds, and we use compound 20. We knew that there are some stability problems with products. For example, quite often they hydrolyze, racemized, or oxidized. So we took our Chimera 20 and we studied the stability under different pH values at pH 5.2 and 7.4. In general, the compound was stable, but the first 8 hours, after 24 hours, we could see that the 20 was decomposed and was significantly decreased and reached the 56% of its initial concentration, while at pH 7.4, it reached 11.2% of its initial concentration. We also tested the stability in human plasma, and we saw that the compound had a half-life of 4.4 hours. Of course, this is not perfect, but the stability profile is sufficient and suitable for further biological testing. Now we synthesized all these compounds, we managed to purify them, collect their data, and send them to our colleagues in Germany, Professor Elmar Wolf and the University of Kiel. He studied the degradation potency of our compounds. Here you can see the results from the high-bid assay. By this assay, you can measure the concentration of your compound inside the cells. And as we can see, our reversing-based compounds were potent degraders of all 3 kinases, Aurora B, Aurora A, and TTK. As you can see here, for compound 13, we have a DC50 of 3 nanomolar, and also for compound 19, it's also a potent TTK degrader. The surprise was that 23, the negative control, also had some degrading activity. They moved to mechanistic studies, and the immunoblotting, they verified that our compounds indeed degrade these proteins, and they made some mechanistic studies using the proteasomal inhibitor MG132, and they showed that the inhibition was mediated by proteasome, but also showed that there was also a mixed mechanism of degradation, especially for compound 23. Then they moved to the examination of the MPS targeting compounds, and here we're expecting these compounds to be selective against the TTK, but unfortunately all of them, they were not active. But our inhibitors SF1, SF2, they worked better. And as you can see here, a very nice result is that the SF1 based compounds, they were potent degraders, but also the selectivity changed towards the Aurora A kinase. So these different structural characteristics give different selectivity against these mitotic kinases. And for the SF2 inhibitor, we see again that the selectivity changes back to the TTK. So for the for the SF2 compound, we see that there is a DC50 of 26 nanomolar. We're quite happy to see these results. Also, the results were verified by immunoblotting. And then we move to the evaluation of cell toxicity to check if our compounds, they are inhibitors of cell proliferation. They used MV411 cells, which are leukemia cells, and this that we saw is very good results. Azareversin and also SF1 compound, they were potent inhibitors of cell proliferation. For SF1, we have an AC50 of 28 nanomolar, and even better, there were results for our products. And I say this, okay, might lose some activity. We have an AC50 of 39 nanomolar, but these compounds are large, and these are very good results because they penetrate the cell membrane, and the activity is very good. So just to summarize, we synthesized 28 proteolytic products. The coupling reactions were they had low to good yields. We could identify another azareversin-based TTK with a DC50 of 18 nanomolar. If we change to SF compound, we see that the selectivity changes towards the Aurora A, sorry. So our studies indicate the importance of the linker. First, for the formation of the tertiary complex, but also we see small changes changing the efficiency and the specificity of our compounds. Now, the mechanism of action is not fully elucidated, but this that we know is for sure that we have developed compounds with potent anti-proliferative activity that are suitable for further examination for anti-cancer research. And of course, I have to thank my students, Elena Sflakidou and especially Christos Siokatas, for their work on the synthesis of these compounds, and of course our colleagues from Germany, Elmar Wolf and Bikas Athikari, for the nice results. And of course our work was supported by OpenScreen GR. And thank you for your attention.
Thanks very much, Vasiliki, for a very interesting lecture, very beautiful results with these large molecules, which I can imagine are very difficult to make. Lecture is open for questions. So again, for the participants, you can put your questions in the Q&A. And for the speakers, they can just use the raise hand tool. I had a question myself. So you told us that the linker length and linker nature is very important. Is that does that affect the binding to the ubiquitin, or is that affecting the degrading of the whole complex? What makes it so critical, this linker length?
Okay, the thing is that the linker it's important because it allows the formation of the tertiary complex between the protein of interest and the E3 ligase.
I see.
Okay.
Yeah.
Of course, if you change, for example, the nitrogen here, pomalidomide, maybe it affects also the activity of the ligase, but the most important thing is the formation of the tertiary complex, and this is very hard to predict in accuracy. That's why you have to synthesize all these compounds, you know.
Exactly. That's what you see in literature in general. This linker design is.
This is the problem. You might synthesize 30 compounds and they may all be inactive, or you might use this anchor that recognizes this ligase, but maybe this is not a suitable ligase for your protein. Okay. So
Thank you.
Yeah.
I see that Dimitris Georgiatos raised his hand. Please go ahead.
Thank you very much, Marshall, for this very interesting talk. Well, I have a question. I wonder if there are any ways to follow the localization of these compounds within the cell. I mean, are there any reports about transforming these products by the introduction of a fluorescent, let's say, dye or?
Yes. I think yes. There are some trivalent products that they are activated inside the cell and photoactivable. You know, you can photoactivate. Yes, but then the molecule is bigger. Then you change many things. You know.
Yeah.
Okay, you can see you can prepare some trivalent to have a fluorescent tag. You know, huh? This is what you mean.
Yeah.
There are some cases, but
well, for mechanistic experiments.
Yes. For mechanistic experiments, yes.
Okay.
It's hardcore biology here, you know. Biologists have many experiments to perform. But it's
okay. Thank you, Vasu.
Thank you. I see there are no other questions. It was a very clear lecture. So then thank you once again. And we continue with Gerasimos Rassias. So can you bring up your...
Hi. I don't know if you can hear me. Right. Can you see my
I think it's coming up. Yeah, we now see your screen or your presentation actually.
So this is here. My internet connection is unstable, but hopefully.
Well, we do hear and see you currently, so it's doable. But your presentation is not on full screen yet. Did you use share screen?
It is on my screen.
Yeah, but I think you have to not share your presentation, but share your screen.
Don't share. I'm sharing. Sorry, I'm sharing my screen. Yes.
Okay. Let's see. Yeah, now we have your presentation full swung on the screen. Can you also change slides?
Yes. See?
Yeah, but we don't see that. Yeah, it works. Yes. Yeah. Go ahead. I have the impression that your audio is not so good.
It was fast. It was too good. Yeah.
Oh yeah, I was maybe too impatient as well. Okay.
I'll try. Yeah, my connection seems to be problematic, but hopefully you can hear me by now.
We do hear you, yeah.
Yeah, can I start?
You can start.
Maybe you could stop your camera.
Right. Thank.
Oh yeah, if you indeed stop your camera, then you
Yes,
have a
you're
bit more
absolutely right.
more bandwidth to spend on audio. Yeah.
Excellent. So, first of all, I'd like to thank you for the invitation, and it's a great honor and privilege to be among an excellent lineup of speakers from Greece, the best in the country. And before I start, I would like to familiarize you with what we do in our lab. This is a picture from our website. So we do a lot of projects on medicinal chemistry, particularly antivirals, anti-cancer compounds, and CNS for compounds for CNS disorders. We also do, because we want to scale some of this for further studies, large-scale synthesis of certain compounds, and sometimes in collaboration with companies for generic drugs, we'll look for new, more efficient synthesis that could be scaled up. And from this exercise, we identify problematic or underdeveloped reactions and transformations that we could perhaps address with catalytic technologies, so we can then reinvest into the synthesis of molecules, both in small and large scale. So today's talk is under this category here. But we'll try to do something on large scale, and as you see, is not straightforward. So the molecule today is sitagliptin, and I will talk for a few minutes about that, highlight the viability issues with the current synthesis, describe the commercial synthesis by Merck, and then present some of our own approaches, and I'll close with a summary. So sitagliptin is a potent selective PDE4 inhibitor. It's a treatment of choice for type 2 diabetes. And since its launch in 2006, it's become one of the biggest blockbuster drugs ever, with a revenue of more than $6 billion a year. And of course, you can imagine that sparked a lot of interest among generic companies after 2017 to get a slice of that pie. But also, it sparked interest among the academic laboratories simply for the sheer joy of synthesizing this compound. You see, this is a beta amino acid.
Jerry, I have the impression, Jerry, I
I
have the impression that the slide changer doesn't
easy.
work. I have the impression that the slide changer doesn't work because now you are at the next. Now,
what do you see now?
I see now your overview slides. And now I see your sitagliptin. Yes. Okay.
I've gone to the next one. All right. Okay. Hopefully I don't have to repeat these numbers. This is the structure. You may think at first glance that this is an easy molecule to make, just one chiral center. It's actually the monophosphate monohydrate salt, which is the API. And a nice review by S.G. Davis back in 2015 described a lot of the synthesis among academic labs, but for us, not all syntheses are good. And because of my background in process chemistry at GSK, and this is principles I'll try to instill to my students, that a good synthesis should not have these drawbacks that you typically see with academic synthesis. In fact, our reference are always industrial synthesis and syntheses that don't have these issues. For example, this is Merck's commercial synthesis, which starts with this acid. Has it slide turned to Merck synthesis? Sorry.
Yes.
Right. So first it's condensation with meldrum acid. You isolate the salt, the Hünix-based salt of this keto diester, exposed CFA, protonates, deprotects, decarboxylates to the cation, and you put the amine in, you get the amide. This is all one pot reaction. condenses with ammonia surrogate from the enamine, and then asymmetric hydrogenation. This is actually, there's two more steps hidden here because this wasn't commercially available at the time. There's two more steps to make this from the bromo aryl compound. So I'll teach to my students in our MSc course in asymmetric synthesis that asymmetric hydrogenation is the queen of reactions. Nothing beats it in terms of efficiency or greenness, because this is the greenest possible. After today's talk, I think Professor Vassiliou Giannakis' work with singlet oxygen comes to claim the title of princess of reactions, because it comes close to these credentials. I mean, look at this loading. This is lower than impurities that you usually get in drug molecules. Merck, in conjunction with Codexis, developed also a transaminase enzymatic reaction where you install this in one step. But this was not a natural transaminase. This was an engineered one. So the cost of making this from scratch and scale actually was not better than the standard chemical process. So this is the registered process. So this is a 7-step overall synthesis, Knock-Holmes, one-pot reactions, etc. So we wanted something similar, if not to kind of beat Merck's process, but at least we can apply some of the process chemistry principles to at least produce the better academic synthesis. And our approach was to reveal this chirolamine from a hydrogenolysis of this oxazolidone, which could come from a conjugate addition of the carbamate at this point. We also considered making this in one step from a nitrine CH insertion reaction, but to cut a long story short, we made this molecule and we tried all catalysts and available, rhodium, silver, and we can never get this bond to form. So let me go back to this synthesis where we use the first step of Kraft's reaction. We use the trifluorobenzene as a solvent, works better. And we can recycle this because it boils at about 90 degrees, and we can use it for the next batch and so forth. Esterification, don't touch the double bond. And then reaction with various cyanates give us mixed results. The best was the paramethoxy one, which gave us a single distereoisomer of the cyclized product here. Excuse me. Second best with the benzoyl and benzoyl, which gave us a 3-to-1 ratio here. And next, hydrolysis of this ester, activation, amide formation, gave us this in modest yield. But before we optimize this, because we can do better, was to test the key step. Unfortunately, it's at the very end of the synthesis. But this never happened. We could never cleave this bond, no matter how many different catalysts and hydrogenase, this transfer hydrogenation, silanes, you name it, we've tried it. So we thought perhaps we need to make this more electro-withdrawing here and perhaps use a lacton rather than oxazolidone. So we modified our approach to sitagliptin from, obviously, from this amino acid, where this could be revealed from the corresponding lacton here. This is the lacton that we're aiming for, and install this nitrogen atom via Curtis or Hoffman rearrangement for this carboxylic acid. This is paraconic acid derivative. And this is also very useful because it's flexible, because it gives us the option, it gives us the option to open this lacton first and then reduce the hydroxyl, because we thought it would be easier to do that rather than the cyclic system, and then do the Hoffman or Curtis step last. So this blue route does the reduction first, Curtis last, whereas the green route does the Curtis first and the hydrogenolysis last. The Carlos Center is set up with this, obviously, reaction, which is a Pinder variant called Wittig-Loller, where the analate attacks aldehyde and all the corresponding alcohol cyclized on the other carbonyl. And we chose this because we had experience, we and others had developed organocatalysts for this transformation or a similar one. Well, this is a more acidic proton rather than that, but that's still, it gave us confidence that we can modify this to make this work asymmetrically too. But before that, we need to figure out if the racemic synthesis worked. So exposing this to PEX gave us this in a 75% yield, 2 to 1, but it doesn't matter because we're going to destroy this chiral center here. So we tried to do the Curtis reaction first, but no matter what we did, the molecule decomposed, presence or absence of alcohols, no joy. So we thought we could make the primary amide here and try the Hofmann reaction, because that is more, you can do this in milder conditions, so you can avoid the degradation. However, everything we did to activate this acid led to decarboxylation. You can imagine any nucleophile here, the activated species releases CO2. This is the carboxylic acid. So we went to our plan B, making the ester, both methyl and T-butyl ester, and then try the hydrogenolysis of this bond on the close one, reversing the order from before. Again, this didn't want to know at all. Just stayed there looking at us. So we went to plan C, which was to hydrolyze this first and try to reduce this bond. But again, no joy. So we decided to make the ester, the amide on this end here with a sitagliptin amine. Again, no joy, because everything we did to activate the acid here immediately shot with the hydroxyl group back here, giving us back the paraconic ester. So this was a dead end, and we abandoned this. Next, we like this idea of installing this by a Hofmann or a Curtis reaction, because they occur with retention of configuration, and well, it was easier to make something like that. Indeed, you can make like that if you disconnect here by an asymmetric Hayashi Miyara hydroaerylation of this bond with the boronic acid or ester in one step. And this substrate you can make easily with, at least in theory, with the amine on interconic anhydride that selectively opens to the non-conjugated carbonyl, of course. We also like this intermediate because it allows us another flexible plan B, because this chiral center here, you can set it up by the asymmetric hydrogenation of this unsaturated species, which you can form by a Heck reaction here from the bromo aryl and the same unsaturated substrate that we use for the Hayashi. So this was a key target. And before I tell you about the synthesis, I need to address a few aspects of the Hayashi reaction. It works exceptionally well for beta substituted acrylates and ketone, alpha beta saturated ketones and esters with aryl groups here or aliphatic, whatever. It works pretty well. This is an example from an industrial synthesis on 3 kilogram scale. But in our case, we have an alpha branched acrylate where the hydroaerylation reaction will produce this chiral rhodium enolate, and the chiral center is set up at the enolic carbon, the alpha carbon, which is configurationally much less stable than the beta carbon in these cases. So this is a soft spot. And that's why you don't see many examples of the Hayashi reaction with this kind of substrate. And the few that you see demonstrate how sensitive the reaction is, the E is here to the proton source and the solvent. Regardless how good the ligand is, if you don't get this balance right with the pKa of the proton source and the solvent, you can have anything from 0 E to high E's. For example, here they found in this example, phthalimide was the best proton source with high E's. So with that in mind, we made this intermediate. It's not as easy as it's a bit tricky because you can get a lot of conjugate addition of the amine here, but we have managed to find conditions where you can get this crystalline and very pure 86% yield. And we did make all three esters, the benzyl, the methyl, and the t-butyl, because it's demonstrated that they affect the ester, affect the size of the ester, affects the E that you get. So we tried the model phenylboronic acid because the trifluoro that you'll see in a minute is terribly expensive. So we tried and optimized these conditions with the model phenylboronic acid. And indeed, we got 92% E and 40% E. And we thought we should, surely, it wouldn't be long before we open the champagne here, right? But when we tried all three esters, the trifluoroboronic acid, there was no reaction at all. So we don't know. We revisited, obviously, all the catalysts, the chloride, the hydroxy, rhodium complexes, proton sources, solvents, you name it. It never worked. We even made our own boronic acid and boronate esters, and we could never get this to work. I'm still not sure why this behaves so differently. So we got at this point, but we still had the plan B, which was to construct the same desired saturated compound by two steps, first with a Heck reaction here, and then to hydrogenate it rather than one step. And this is not the first choice of conditions, but we did screen some conditions, and we arrived here, which gave us at least 100 millimolar scale, gave us a very nice conversion to this product. I will decide to scale it up, which is this is our goal, scaling up and working robustly to 1 gram scale reaction. We saw things. You see, these are still present in the small scale reaction, but when you do large scale business, everything magnifies. The all problems magnify. We get this, and we look deeper into what was forming. And here, this is the isomerized product, star material. The double bond is here, and these two shoulders on the HPLC are is the isomerized product, cis and trans, and well, the double bond is here, and this is saturated. One thing is happening is we can see this happening just by this first isomerization, just simply by adding base to the substrate. So our substrate is base sensitive. You can get away below 40 degrees with the low bases, but above 40, and we require high temperature here, this is unavoidable to a certain extent. But because we have seen reactions that go to completion, we believe that this slowly goes back, summarizes less readily, but still does. That's why you can end up with no star material at all. The other byproducts are much more complicated to consider because the intermediate you get from the Heck reaction, obviously the saturated one, align the chain so you get a syn relationship with the palladium, so you get a better hydride elimination. So if you get elimination from this side, which is the desired product, you get desired product. Well, if you get elimination from the other side chain, you end up with a isomerized product, which can still base isomerize to the minor isomer. Perhaps it's I'm not saying this is only this way forming, but it can also be forming from this compound as well. So we did go back and tested all permutations and combinations you can see in these in terms of ligands and palladium catalyst, bases, and temperature and solvents. And oddly enough, dioxane at 130, which means under pressure, makes a lot of difference in the performance of the reaction. We've seen this pressure effect before in a previous work on Heck reactions on different substrates. And it was actually documented in the literature, but no one knows why there's such a pressure effect. Maybe it's like the Diel solid reaction where the transition state is more compact and then deflates as the product forms. But the pressure does help. And the best conditions are these in this combination of reagents in green. And this gave us significantly suppressed isomerized product and star material. But think on this 2.5 gram scale reaction. But we develop, obviously, we do with all reactions, recrystallizations that allow us, in this case, to isolate pretty clean material from this mess. This is the NMR of this compound. So we're happy with that, because that's allowed us to end this synthesis, at least. Here is the racemic version of it, hydrolysis of the ester, forming here the saturated compound by palladium catalyzed hydrogen, that's succinimidyl carbonyl, and reacted with ammonia, generated controlled in situ to give us the primary amide. And this with iodobenzene diacetate produces the Hofmann rearrangement in excellent yield. This is racemic sitagliptin. We also tested the alternative path, which is to make the amide first. This also works, same conditions. And also the hydrogenation of the amide also works to give the same intermediate. So this is a 7-step synthesis of racemic sitagliptin. It requires no chromatography at any of the previous steps or on any of these. The low yield is because of the Heck reaction was about 30%. So if we double that from converting all the isomers to the desired one, this will double. But also offers the opportunity for classical resolution if one wishes to. However, our goal, which is ongoing work as we speak, is to introduce this hydrogenation steps with the chiral rhodium complex. There's plenty of literature. We're confident we can do that very easily. Literature, this is bread and butter for rhodium. We have a lot of chiral ligands to try. Although we would prefer to go via this route, because once you set up this chiral center here, this is retention configuration. You don't expose it to any bases or acids for this to have a risk of epimerization. Therefore, our work is now centered here, and also in optimizing the Heck reaction to improve the yield. So hopefully, in the next couple of months, we'll have this done and dusted. I know this is famous last words, but I think the hard part was the Heck reaction and the Hayashi, the failed Hayashi reaction, which we owe to revisit. So, summary, I think I tested several routes. We tested a lot more, but didn't have the time to go through them today. And we did learn a lot about this. There's not such a thing as an obvious easy reaction or easy molecule when you try to do things in large scale with a lot of constraints to what you use and no column chromatographies. And we demonstrate the feasibility on gram scale for racemic sitagliptin, and we'll try to improve on that. I do want to thank my group, because we have a big group, usually about 15 to 18 people, depending on the year. But there are certain players in the sitagliptin effort that I would like to thank. This is Fotni, Maria, Nick here. There are also some past members that worked, which I'd like to acknowledge because we did a lot of previous work. And I realized all of these people, including Ioana, which is now a PhD student of mine, when she was an undergraduate, she also worked on sitagliptin. And now I realize how cool I was with my students assigning them to this project, because as you agree with me that it's not easy, at least the way we want to make it. So Ioana is now doing the PhD on a different subject, but she was happy to volunteer and be the one to finish the job with the asymmetric hydrogenation. So thank you all for your attention. I wish I had more time to say about the other failed attempts. The Journal of Failed Chemistry, my supervisor has said, once you learn. So with that, I would like to thank you for your attention, and I'll be happy to answer any questions you may have. Thank you.
So, Gerasimos, yeah, we all learn from dead ends and detours. I also know what it is, but it's super interesting to listen to this story, which is now open for question. Who can I give the floor, or who wants to put a question in the Q&A box? I had a question myself because we also worked on aryl boronic acids. We also worked on aryl boronic acids, and I wondered in this, let's say, failed boronic acid additions for the trifluoroaryl boronic acid. Is it proto-deboronation that what you're suffering with? Do you find back the trifluorobenzene?
Yeah, we did look at that because, as you said, it's a common problem, especially with eroded under these conditions. Other people reported when we looked at that, we didn't see, well, at least in the absence of catalyst, any proto-deboronation. We didn't. It just appears to be inert. Yeah, the proto-deboronation wasn't the issue with this reaction.
I see.
But it does happen, as you say. It's quite frequent.
Okay.
And I was surprised because a lot of people say this particular the fluoro substituted benzene rings boronic acid is are. But again, this is not only acidic conditions of benzene, it's just a phenol or phthalimide. So in terms of pH, it's pretty mild, and that helps.
All right, more questions or comments? I see that's not the case. Then thank you once again for disclosing this lecture, and then we move on to Professor Alexandros Sografos from Thessaloniki.
I forgot to thank you. Sorry, my screen just frozen. I didn't hear anything, but thank you.
Thank you so much. Thank you so much for the invitation while I'm trying to share my screen. I hope I can succeed it.
Yeah, we do see your presentation and it's now full screen. So if the slide changer also works, yes, it also does work. So you're right to start.
Perfect. Thank you. Thank you so much for inviting me in this beautiful event. And of course, I want to thank EuChemS, Yannis, for giving this kind invitation to me, of course, Adri and Pat for inviting me here. So before I start with the topic of today's presentation, I would like to spend a couple of minutes in order to give you an outline of our research at Aristotle University of Thessaloniki. As you might be aware, we are interested in natural product chemistry because we believe that structures like this are ideal in order to develop novel chemical reactivity. So our dream is to make total synthesis as easy as solving a puzzle. So what we are actually doing is that we are trying to invent new reactions through total synthesis. And as you will find later in my presentation, we are also developing libraries of natural compound for biological screening. Natural products were and continue to be one of the major sources of drugs candidates, but unfortunately, we cannot really find them in really good quantity and purity. So what we actually have in hand in order to synthesize them are two major strategies. The first one is the target-oriented synthesis that we all know as total synthesis, and the other one is the divergent total synthesis or collective total synthesis. And what we are actually trying to do by utilizing collective total synthesis, we are trying to combine target-oriented synthesis with diversity-oriented synthesis and develop a homostatic intermediate and utilize it not just for synthesizing one natural compound, but instead a collection of natural compounds. And this is the method of choice of our group in order to do total synthesis. And I want to share with you some highlights from the pyridine alkaloid family of compounds, where Anna, that you see in the photo, she managed to develop a homostatic intermediate in the form of this blue compound, and she managed to access all this carbogenic complexity that you see in the slide. She managed to do 3 total syntheses. She accessed 5 different carbocyclic cores, 50 members library of compounds, and we were fortunate enough to find that 2 of them were actually good for antibiotic activity. So let's move this kind of logic now in a much more challenging category of natural compounds. This is the sesquiterpenal family of compounds, and probably you are aware of this family of compounds from the molecular complexity But I want to highlight also the biological properties of these compounds. And I have in here, I'm highlighting 3 compounds, thapsicarcine, parthenolide, and artemisinin. And all 3 of now are in clinical trials for anti-cancer activity. And I want to point out that they are quite diverse also the way that these molecules are acting. So thapsicarcine inhibits SERCA pump, which results elevated calcium level inside the cell and leads to apoptosis. Artemisinin, which is probably you all know from its antimalarial activity, has also really unique properties as anti-cancer compound by inhibiting VEGF factor 4 angiogenesis. And the last one, parthenolide. Parthenolide was really unique for us because this was the one that initiated our project. Parthenolide was found to selectively inhibit cancer stem cells while sparing normal ones. And what biologists believe is that this compound is acting through the inhibition of NF-kappa-B signaling pathway. And this was really a good information for us, because if you search the literature for sesquiterpenoid lactons, you are going to realize that many of the sesquiterpenoid lactons are actually inhibiting NF-kappa-B signaling pathway. So what initiated our project is to make, if it is possible, a really diverse library of sesquiterpenoid lactons and seek for new leads for anti-cancer activity and more specifically inhibition of cancer stem cells. So let's give you some more details about the structure-activity relationship of these sesquiterpenoid lactons. Of course, you're realizing that we are talking about sesquiterpenoid lactons, which means that you have a lacton portion in this kind of molecules. You are going to find several lactons, but the most important of them is the alpha-methylene gamma-butenolide core that some of these sesquiterpenoid lactons are bearing, because you are going to realize that the most potent members of this family of compounds are bearing the alpha-methylene gamma-butenolide core. What this means is that the actual electrophilic core of this alpha-methylene gamma-butenolide is the important one by interacting, what they believe is that interacts with cysteine inside these molecules in order to make covalent bonds and initiate the biological activity. And you can find quite alpha-methylene gamma-butenolide lactons. You can find them in 2 radioisomeric forms, the 6-12 lactons that you see in here, and also the 8-12 lactons that you see in here. And what this actually means, 6-12 and 8-12, is the way that this lacton moiety is cyclized within the carbocyclic core. And talking about the carbocyclic cores, you see that we have different carbocyclic cores within the sesquiterpenoid lactons. So you can find either 6-6 members, 5-7 member rings, 10 member macrocycles, and many more that you are going to see in just a few minutes. Another thing that I want to point out is this crucial stereocenter that you see in many of these natural compounds in the junction. And this is really important because if you need to have a really unique and diverse library of compound, you need also to address somehow this stereoselectivity, because in natural products you can find both stereoisomers in this portion of the molecule. So the big question that arises is it possible to make divergent plan in order to access not just few of the natural compound, but the whole family of the natural compound? And what else I thought to do is actually what nature does. And what nature does, that starts from farnesyl phosphate and goes along 2 distinct phases. In the first phase, farnesyl phosphate cyclizes to germocrans and elements, and in the oxidized phase that precedes this process, these carbocyclic cores are decorated with allylic alcohols or epoxides. A second round of cyclized phase takes these molecules now and transform them to udesmanolides, guanolides, cadenanolides, and lindenanolides. And a second round of oxidized phase further enrich this kind of diversity. So if someone wants to mimic this kind of procedure, what needs to do, of course, is a divergent synthesis. But what might be the homostatic intermediate to utilizing this divergent synthesis? And what else I thought to search for compound is the germocranolide compound, the 10-member macrocycle. And actually she found one the one called furon-germanon. Furon-germanon is not really a random compound, but brings special features. The first one, as I told you already, is a germocranolide, which means that you have a 10-member macrocycle, and 10-member macrocycle enables enough flexibility in order to produce other carbocyclic cores. The second thing that bears a furan moiety, and a furan moiety can be regarded as protective form of the lacton moiety that you need for the biological activity. And the last thing is that it is in rather low oxidation state, which means that you can further induce oxidation steps in order to induce the complexity of your family. So as soon as cells are recognized this potential homostatic intermediate, what it needs to do, of course, was to synthesize it, and this was the first total synthesis of furan-germanon, starting from carbon in just 9 linear steps, 8% overall yield, we managed to synthesize it. And the key reaction to this process was a highly non-selective oxycope reaction in order to break down this 6-member ring in order to expand it to this 10-member macrocycle. Okay, we had in our hands the potential homostatic intermediate, but what actually does it mean to have a homostatic intermediate in your hands? What means is that you have the ability to induce complexity just by utilizing simple reactions, just 2 or 3 steps away from the homostatic intermediate. And I want to highlight some of these complexity that we can access. So as I told you already, we managed to transform the 6-member ring to the 10-member macrocycle of furan-germanon, but furan-germanon can also access, let's say, this 6-member through a oxidation cationic rearrangement. Or if you go back even from the pinpoints of this pyramid, you can access this 3,5,6 through cycloisomerization. So let's give you some more details about this kind of procedures. So we synthesize this advanced intermediate compound 8. And if you take this compound and just heat it up 140 degrees Celsius, then the first reaction is the oxycope reaction in order to produce furan-germanon. But if you take it even longer, you're going to have a sequential in-type reaction in order to form this beautiful 5,7 guan core. And this compound, you see that we can access it in high selectivity on the other isomer. And this compound can serve also in its own right as a homostatic intermediate in order to form other complexity. So if you leave this compound open in air and you have enough patients, after 2 days, you are going to have the first total synthesis of this beautiful compound, compound 15. And also, the same guan, if you just treat it with TFA, you can retro in order to have access now to the Z germochrome. So we have access of both E and Z germochrome, and this is what we believe actually to be a biosynthetic also process. What else can we do? Okay, we can see that furan-germanon, our homostatic intermediate, has alpha position to a ketone, 2 positions, and you can have the ability to oxidize either the 4 or the 6 position of this 10-member macrocycle. Let's see how we do for the 6th position. With kinetic control, butyllithium oxaziridine, you have access to 6-hydroxy furan-germanon, and then heat it up 140 degrees and again, and you have the first total synthesis of the dorol. And what about this intermediate? Can we use it? Yes, you can treat it with just PTSA, and you can have a cationic oxidative rearrangement in order to have access only to this compound arteaminine, which is actually a precursor of artemisinin family. So you see that we are utilizing really simple conditions in order to make all these differentiated transformations. What about the 4th position? The 4th position can be accessed through thermodynamic control. So KHMDS followed by dioxygen, you can form now the 4-hydroxy furan-germanon. And if we never isolate actually this, we just heat it up at 140 degrees, and you have the first total synthesis of guaiacol. Okay, let's give you one more example of how we are accessing complexity. the advanced intermediate just with platinum chloride or with gold chloride, you can initiate 1,3 or 1,2 migration of the acyl group in order to have these beautiful molecules of 3, 5, 6 member rings of the miliol family or the lindenanolide family. Okay, probably you all gonna agree with me now that ELSA succeeded to make a lot of carboxylic complexity in this kind of transformations, and she succeeded so many things. But if you take a closer look to this pyramid and the highlighted parts of this gray part that all these natural compound that she prepared, what we can see is that she did well with the carboxylic complexity, but what about the lacton moiety? You see that we accessing lactons or furan moieties, but we never actually succeeded of preparing alpha-methyl and gamma-butanolide cores. This was actually a big drawback because this was the most important from the biological activity family of compounds that we needed to incorporate in our library of compounds. So as soon as we realized this drawback, of course, we needed to somehow change the plan, and this was the first generation synthesis starting from this advanced intermediate, and we thought, okay, if the problem is that we cannot really transform furan ring to alpha-methyl and gamma-butanolide cores, why we cannot really incorporate it just from the beginning? We thought, okay, let's change the advanced intermediate to this compound. And if we are actually starting from the beginning, why we cannot also access the radioisomers of the 6,12 lactons? Probably you all gonna agree with me that the most simple way in order to make retrosynthesis of this compound is by making a direct lactonization from carbonic acid. This was also a natural compound. Then somehow protect the highly electrophilic system of alpha-methyl and gamma-butanolide cores and introduce stereoselectively the upper part of the alkyl chains in order to have these advanced intermediates. Actually, we managed to do pretty well in these procedures because Maria joins the group, we joined the group, managed to make a lot of contribution in this field. So we managed to synthesize this compound. We are going to see in just a few minutes how we succeed that. And this compound now had the ability to return to the furan moiety in order to prepare this compound in just 3 steps. So we have access to all this complexity that ELSA did, and we have now the ability to go even higher in order to access the alpha-methyl and gamma-butanolide cores. So how we did that? Starting again from carbon, with TMS chloride and oxone, we managed to make chlorination in this part, hydrolysis in order to have the allylic alcohol, and then oxidation in order to have the carbonic acid. Carbonic acid was actually known in the literature, and we were not really able to make a lot of it after repeating this kind of procedure from the literature, because we went down to less than 5% overall yield in order to synthesize it. So what you see in there is a completely unique procedure in order to prepare carbonic acid. And then we needed somehow to make the lacton moieties. We needed somehow to cyclize this portion of the molecule from the carboxylic acid in order to have the 5 member rings. And we tried everything. We tried every condition that exists in the literature in order to make allylic oxidations, White's procedures, Wu procedures, and so on. And we never succeed of making any of this hydroxylation in this part of the molecule. And the problem was that this part of the upper part of this molecule is quite unstable. So finally, what we thought to do is to utilize carboxylic acid as a radical initiator. And we thought that if we can make a radical and survive extrusion of carbon dioxide, maybe we have some chances of this radical abstract a hydrogen from this portion, the most stable portion, in order to have the cyclization that we need. And actually this works really nicely, because if you treat this carbonic acid with PIDA, iodine, and light in a modified Suarez conditions, you are going to have compounds 8 only this isomer and not the 612 isomer on the other side. And then we protect it with methoxy group, and we transform the upper part in order to introduce the alkyl chains that we need in order to have the advanced intermediate 3. And 3 works beautifully, because if you take and heat it up 170 degrees now, you are initiating again oxy-cope reaction in order to form this germogranulite, and then in-type reaction. Actually, this is in equilibrium in order to form this guanolite. And this guanolite, now you see that we have the protection of the methoxy group in the of this part, in this part of the molecule, in order to readily deprotect it and make the alpha-methylene gammotenolyte codes. And this molecule work nicely in order to produce a lot of complexity. So our plan was to take this advanced static intermediate, this common static intermediate, and utilize it in order to make really simple reactions like reductions, dehydration, and oxidation in different sequences in order to just have a lot of complexity in our hands. And the most interesting molecules of this part are the more oxidized molecule, because if you are going higher in the oxidation state, you are going to see many transformations that you even not imagine. So I want to give you some recent results that we have in this part of the project. So we had the ability to access hydroxy epoxides or hyperoxy epoxides, and these molecules are really interesting because you can open up the epoxide portion of these molecules quite diverse. So if you treat hydroxy epoxide with just PTSA or bismuth triflate or other Lewis acids, then you are going to have opening in this part in order to form the cation, and this cation, then by oxygen, you are delivering guanolites of this type. But if you go and treat the same exactly epoxide with BF3, then you are opening on the other side and only on the other side, and then you have a semi-pinnacle rearrangement in order to have the formation of these pseudoguanolites. And this is really interesting in our view, because it was known in the literature that biosynthetically pseudoguans are coming from guans, but no one succeeded to make this kind of transformation. So we're really glad to see this happens. So another thing is that if you use exactly the same compound forming in here, not the hydroxyl group, but the peroxy group, and you make exactly the same condition, BF3-8, then what you are doing is that you are initiating a Hook-type cleavage in order to have breakage of these bonds and then accessing secoguanolites. Secoguanolites were also known to be produced from guanolites, but no one succeeded to transform these kind of intermediates to secoguanolites. And you see that we managed to have all the isomers of this type, and it is really interesting to find out that depending on the isomeric part of these compounds, you can access quite selectively these beautiful compounds. So we have accessing now to pseudoguanolites, secoguanolites, or even xantholite type of compounds. So what else can we do? Of course, we can do exactly the same chemistry for the 612 lactons. You see the chemistry that we are talking about is quite similar to the one that I already showed you. We had the ability now to build this advanced static intermediate, and this advanced static intermediate, if you just heat it up, then you have access to guanolites of this type. But most interestingly, these compounds are quite diverse. So if you take advanced static intermediate and you just heat it up without any Lewis acid, you are going to have access majorly to compound 10. But if you treat them with lithium chloride, then you have formation majorly of compound 13. And you see the difference between the two molecules are the adjacent stereochemistry in the junction of these molecules. So this was really unique to find, because we can now stabilize the intermediate state in order to diverse this kind of in reaction in order to produce either of the both of these isomers. And as you see, Calliope is very happy in here because she managed to also access some natural compounds in her own. Okay, let's sum up a little bit. So what we can do is that we can have really diverse structures. We have the ability to produce lactone moieties and alpha-methyl and gamma-butanoids. We have the ability to diverse in this portion of the molecule in the junction, which is really important. But is it over? Do we have the solution in order to prepare, let's say, thapsicarcine pretty easily? Actually, no, we cannot really do really easily, because the problem is that we can never have enough ways to make selective oxidations. And I think that this is the most difficult part in total synthesis, in order to have really selective oxidations in really complex molecules. And in order to address somehow this kind of lack of selectivity in the oxidations, what we thought once again to do is to do what nature does. And what nature does, that takes this kind of carbocycles and go in mitochondria. In mitochondria, you can find really impressive enzymes in the form of monooxygenases. And what monooxygenases are doing is that they are taking oxygen in the presence of a reductant, a reductase, NADH or NADPH, and these reductase are actually reducing the oxygen to peroxy in the oxidants that make the substrate to be oxidized. And usually monooxygenases are associated with cofactors, and you can find cofactors like organocatalytic cofactors like flavins, or you can go in higher oxidation states like using EuChemS, like metal cofactors of iron or copper. And we thought, is it possible to take also carbocyclicos and go and make this kind of transformations with much more simple terms? And actually we can do that, because if you take really simple alkenes in the presence of this organocatalyst, pyrrole proline ketoperazine, and you mix the alkene with pyrrole proline ketoperazine in the presence of dioxygen and a reductant, in our case hand ester, you are going to see that oxidize efficiently the alkene to epoxides. And this also works in the presence of catalytic amounts of selenium dioxide in order to produce the allylic oxidations of these alkenes. And this method, diketopiperazine, is actually doing similar work of what flavin is doing. So diketopiperazine, in the presence of dioxygen, is activating dioxygen in order to form nucleophilic species of this type, or hydroperoxides, electrophilic species of this type. And these are the actual oxidants of the process. And as soon as this oxidant is coming in the surface of a substrate, oxidize it and make hemiaminal. And this hemiaminal is broken down and reduced by hand ester, which is the biomimetic variant of a reductase, in order to have again the recovery of the cycle that we need. And this epoxidation works really nicely because it tolerates a lot of substituents, and most importantly, in our case, it is quite selective because you cannot really access through this epoxidation the terminal alkenes. And this is really important because you can now expand this kind of methodology to allylic oxidations, because if you take exactly the same methodology with DKP dioxygen in the presence of selenium dioxide, then you can make allylic oxidations of alkenes. And this method works even more efficiently than the classic Sharpless allylic oxidation reaction. And in order to highlight the ability of these oxidants, of course, we needed to test it somehow. And Kiki, you see there that she's really happy. We managed to address a lot of oxidation states of guanolides. And as you see in here, we compared it with the classic protocols of selenium dioxide with DPHP or with MCPBA for epoxidation. And as you see, our reaction is working much better than the classic protocols. And of course, we needed to highlight the ability to make complexity, and Adonis came in our group, and Adonis had a project in order to prepare an established homostatic intermediate in the form of this costunolite. Costunolite was pretty easily prepared through core-race or modified core-race procedure. And what Adonis did is that he took costunolite and he made just aerobic oxidations in order to access at least 13 different natural compounds in a single plan. And what you see in here is all these boxes that you see in here are actual natural compounds. And as you will see in here, the only thing that we are working is allylic oxidation, sepoxidation, singlet oxidation, or isomerization just by utilizing dioxygen. And we can make it even more complex. Antonis managed and Kiki managed to prepare a lot of complexity in the form of these dimers, and now we are trying also to expand it more. Can we make even more complexity from this part of oxidation protocol? We are developing in a collaboration with Miguel Costas now a really unique protocol utilizing DKP, oxygen in the presence of metal catalysis. And what we believe is that we found already a really good protocol making highly selective oxidation just by utilizing oxygen in the presence of metal and DKP. So what we are doing is that we are trying to make divergent synthesis. We are preparing a really diverse collection of natural compounds. And what we are actually trying to do is to make biosynthesis more simple. And I think that this is the most important slide of my talk. These are the guys that they work hard in order to make all this happen. There are really dedicated students, really talented students that deserve all the applause from you. So I want to thank them. I want to thank the funding agencies, our collaborators, and of course, all of you for your kind attention. Thank you.
Thank you very much, Alexandros. It's beautiful to see how this field moved forward in the past few years, but due to your group. And there are already eager people to pose questions. I see Georgios Vassiliou-Giannakis. Please.
Yeah, thanks a lot, Alexandre. I have to agree completely with Andrei. This is beautiful natural product chemistry. Alexandre, I have a question. I'm quite sure that you have tried it, but I just want to make sure. Where you have this endoperoxide and the beta position, the hydroxyl group, to just open it up, it takes 2 days, I think. Did you try to just dump a photosensitizer and just bubble some air and some visible light? Maybe the room light is enough. Just to do it faster.
We tried, but we are not really as good as you are in singlet oxygen chemistry. So what we managed to do is just to ruin our material. So we just left it in dioxygen in order to be oxidized.
That's fine. Thank you very much. Thanks.
Thank you. I thought I saw another hand, but that might have disappeared. So if you think that you want to pose a question, please go ahead or put it in the Q&A box. Yeah, Gary, go ahead.
Hi. I just want to say congratulations to Alex for beautiful chemistry and complex molecules. Perhaps a question concerns the selective oxidation. At some point said it's difficult to do selectively at some of those skeletons. I just want to ask, for the sake of it, if you tried Christina White's catalyst, or if you could ask. I know it's expensive because we tried them on one of these CH insertion reactions, but it's terribly expensive. But I don't know if you had borrow some and try it.
Thank you, Jerry. So of course we tried, and this was one of the reasons that I collaborated with Miguel Costas, because he has plenty of catalysts on his own to test. So we tried every catalyst, and the problem is that you cannot really make really selective chemistry by initiating just a hydroxy oxometal compound with these intermediates. And what we are trying now is to make somehow possible to make selection through different mechanisms. So we don't, of course, have still the solution, but we have some initiation points that we can hope on, that we can make selectivity just by dioxygen and these metal species.
Excellent. Well done, Alex. Well done.
Thank you.
Thank you. Or questions or comments? I see that's not the case. Then thanks, Alex, once again for your presentation. And then we continue with Professor Dimitris Georgiadis from the University of Athens.
Okay, thank you very much. Let me try to, I hope I will be successful here. Okay, so tell me what you see.
We do see the presentation, but not yet on full screen.
And now?
Now I see, but now I see it in presenter mode. So now I see already the next slide too.
Let me hide presenter view. Sorry about that.
Yeah.
What's happening?
Just put it back on, Dimitri.
Yes, this is full screen. If you're now also able to change slide, then we are there.
This is full screen?
This is full screen.
Okay. And
yeah, it just works. Very good.
A moment, because I think. Okay.
Excellent.
Okay, so I think I have a problem myself here, because just give me a minute, because
it does look fine. So I hope you don't change too much.
Okay. So first I would like to, is it okay that the slide transition is okay?
Definitely, yeah. Just go ahead.
Okay. So I would like first to thank. Okay. I think I have a problem with. With the laser pointer here now.
Yeah, we can see it perfectly fine, Dimitri.
Okay. Yeah. So everything is so. So I would like first to thank Professor Likakis for and all the organizers, of course, Pat and Andri, for the kind invitation to this virtual meeting, to this beautiful event. It's really a great honor and privilege for me to be here among friends and discuss about the advancements of organic chemistry here in Greece. And of course, I would like to thank you, Yanni, for the introduction in your starting comments. As already said, I work in the Department of Chemistry at the Laboratory of Organic Chemistry International, Campodistria, University of Athens. My colleague Chris presented very nicely our department, so I will not say more about that. I did prepare this slide about Leonidas Servas, but Chris already said a few words about this emblematic, I would say, figure of organic chemistry in Greece, but also within the broader community of organic chemists in Greece. So I will not say more about that. I would just like to add to what Chris said, that the European Peptide Society established in 1988 the prestigious Leonidas Zervas Award. And of course, we realize that here in Athens, there are some big shoes to fill. But I'm very happy to see that all of my colleagues like Chris and others that are not here today are doing an excellent job to stay at the forefront of organic chemistry. So with that said, I would like to move now to the topic of my talk, which are phosphorus-containing peptidomimetics, a class of compounds that we are particularly interested in, and we are working on that for the past years. So let me first set the context of our work. We all know peptidomimetics as molecules designed to address limitations associated with bioactive peptides, such as poor chemical stability towards proteolysis, poor absorption and transport properties, poor selectivity, sometimes adigenicity, and undesired side effects due to that, or in other cases, to alter the properties of a bioactive peptide altogether, for example, by generating an inhibitor from transforming a peptide substrate. Now, you can see in the slide the different methods to transform a peptide to peptidomimetic. These methods have been classified in 3 different levels: local modifications, secondary structure mimetics, and global restrictions. These can be applied independently or in combination, as you can see, for example, in this peptidomimetic of somatostatin developed by Nicolaou, or this TRH mimetic. Of course, probably the most successful strategy to design first-generation peptidomimetics is to apply at specific points, at specific positions of peptide, local modifications, and this is exactly where we meet organophosphorus peptidomimetics. In particular, in this slide, you can see that there is a huge number of different local modifications that can be applied, and phosphorus-containing peptidomimetics are a class of peptide bond isosters, as you see here, and include phosphonamidic, phosphonic, and phosphinic peptides, depending on the nature of the X group that you can see in this structure, whether it's a nitrogen, an oxygen, or a carbon. Well, actually, the phosphorus moiety that you see here in this structure is not exactly an isoster of a peptide bond. It is more similar to these diol species that you see over here, which resemble the transition state of the hydrolysis of a peptide bond, a property that identifies phosphinic peptides as transition state analogs for proteolytic enzymes. Phosphonamidic and phosphonic peptides were discovered first, and they were extensively used in early mechanistic and crystallographic studies. However, over the years, phosphinic peptides dominated, mainly due to their greater chemical stability and the comparable bioactivity to that of their nitrogen and oxygen analogs. So the question is, what can we do with phosphinic peptides? Why are these compounds useful? Phosphinic peptides are excellent inhibitors of zinc metalloproteases, which is the largest family of proteases in human, serving multiple biological roles depending on the physiological context that they operate. Many of these enzymes are validated pharmaceutical targets, and since their overexpression is associated with many severe pathologies, for example, cardiovascular diseases, diabetes, or cancer. And here you can see the way that phosphinic peptides function. You can see that they mimic the structural features of the transition state of proteolysis by and this transition state, according to the transition state theory, is characterized by optimal interactions between the P and P prime subsites of the substrate and the respective specificity pockets of the enzyme. Now, over the years, our group has used, of course, our group and other groups has used these compounds, phosphinic peptides, in order to produce new drug candidates, to answer biological questions, to gain insight into the mechanism of zinc proteases through crystallographic studies, and more recently to generate activity-based probes or other optical or radio labeling imaging tools for other applications. And if you want to read more about all these applications, please read this review article shown here. Okay, so in this slide, you can see the structure of several inhibitors of some medicinally important zinc proteases that we have developed over the years in various collaborative projects, spanning all classes of zinc proteases, like carboxypeptidases, as for example in this inhibitor of carboxypeptidase A, the selective inhibitor of carboxypeptidase A, endopeptidases, like in the case of this inhibitor of MMP12 or this meprin beta inhibitor, selective inhibitor over meprin alpha, and these inhibitors of amino peptidase at the right part here in the slide. Well, I know that this is a very busy slide and I will not get into more details about the discovery of these inhibitors. However, I would like to emphasize the selectivity that has been attained for the target enzymes using these compounds after many rounds of optimization of these side chains of the phosphinic peptides, the P and P prime positions, as we call them. Now, from a synthetic perspective, a building block approach where a phosphinic dipeptide isoster is elongated using transitional peptide synthesis seems like the most obvious approach to synthesize these peptides, and indeed this strategy helped SAR during early studies. However, it soon became evident that specificity mainly depends on what can be introduced in this part of the molecule in the building block level. So it is clear that addressing synthetic challenges at the building block level is essential to unlock the potential of phosphinic peptides. And to the time that I have left, I would like to share with you some synthetic stories of our group related to this effort. Okay, so motivated by the need to generate broad chemical diversity in this position of phosphinic peptides, the so-called P1 prime position, we proposed in one of our early studies, as you see here, a modification of the most commonly used protocol for the preparation of these structures, which is the phosphomycyl addition of silyl phosphonides derived from phosphinic acids under silylation conditions to substituted acrylates. As you see, this red group over here is actually pre-installed on the electrophile. So we wonder whether it would be possible to introduce these side chains to these intermediate silyl enolates. So we tried different options here, and finally we managed to successfully couple, in fact, the phosphomycyl addition with a nylon glycine rearrangement by using allyl acrylates, which allows the transposition of the allyl group from the ester side to the alpha carbon of the final molecules. Okay, this is not exactly, this is an important first step, but not exactly a post-modification per se. So we thought next that since the reaction happens in the presence of a base, we could probably form the necessary allyl acrylates in situ by using, instead of them, acryloid chloride and an allylic alcohol. And indeed, we observed that the reaction performed well, allowing the use of allyl alcohols as synthons for the post-modification of these scaffolds. So we tried this reaction in different substrates. The reaction worked very well, as you can see here, tolerating a variety of allyl acrylates or allylic alcohols. But what I would like to highlight at this point is the synthesis of these disubstituted derivatives that you see here that obviously cannot be prepared by a classical standard phosphomichael addition reaction. And they are particularly interesting for their potential bioactivity because of the conformational constraints that are induced by this polysubstitution. Actually, we came across the necessity to introduce conformational constraints to this position over here of this molecule during the development of a C-domain selective inhibitor of angiotensin converting enzyme, which has two active sites, one in the C domain and another one in the N domain. And this conformational constraint proved to be a key determinant for the selectivity of this compound over the N domain active site of ACE. So we had to develop a more efficient method that could overcome the slow kinetics of the phosphomichael addition. And we thought that probably an alternative would involve allylic substitution of Morita-Bailey-Schillman acetates, followed by the reduction of the product. Indeed, this protocol led to an impressive acceleration of the PC bond formation and also provided a way to synthesize alpha-beta disubstituted scaffolds, as it is obvious from this competition experiment between a Michael acceptor and a Morita-Bailey-Schillman acetate, which leads only to allylic substitution products, as it obvious in this figure. So we tested the substrate scope of the reaction, which was broad for both alpha and alpha-beta substituted derivatives. Of course, this double bond of the products can be reduced to the saturated analogs, as I mentioned before. However, we thought that maybe such derivatives with which include a Michael acceptor, in fact, their structure, could potentially serve as substrates for further post-modification. And this idea was supported furthermore by two almost concurrent reports appeared in 2016 in Science Journal from the research groups of Ben Davis and Park, dealing with the chemical modification, the broad chemical modification of whole proteins containing dihydroalanine residues in their structure. Even if the reported conditions in these journals were not suitable in our case, these reports was a huge step towards the establishment of Giese-type radical alkylation as a powerful late-stage diversification strategy. And this is exactly what we wanted to do. So the idea was to use these derivatives, the dihydroalanine derivatives, in order to perform C-alkylation by radical trapping using the Giese-type chemistry. Okay, so let's see how did this work. After optimization, we concluded in three different sets of conditions. Conditions A, that utilized ethylborane as an initiator and tin hydride as a hydrogen donor. They work in an open flask, and these conditions seem to be more advantageous because they can work in low temperatures. They are compatible with both iodides and bromides, free phosphinic acids or esters, and in addition, they are compatible with stabilized radicals. Conditions B and C that you see here are tin-free alternatives of condition A. They use either tris TMS silane or sodium cyanoborohydride as a hydrogen donor, and both perform well with iodides However, this silane protocol is not compatible with phosphinic ester, whereas this sodium cyanoborohydride protocol is not compatible with acids. So as you can see here, the installation of primary, secondary, or tertiary alkyl groups by this protocol was possible. And in addition, we were able to introduce protected or non-protected functional groups that give direct access to the functionalized side chains of natural amino acids. Now, raising the bar to more complex peptide-like substrates, we tried to take the challenge to perform the same reaction to these compounds here in a dipeptide level, bearing different side chains in the P1 position and different amino protecting groups. And we managed to obtain the final products in high yields. And in most cases, the final products were isolated after single precipitation. This operational simplicity and high efficiency of this protocol was also observed to the synthesis of these building blocks, which are suitably protected for use in solid phase peptide synthesis, and they are typically accessed through multi-step laborious routes. And at the last step of our optimization, in order to verify the potential of this method as a synthetic machinery, as we attempted to illustrate in this artwork over here, we tried this late-stage diversification to the level of tripeptide, of a phosphinic tripeptide. And despite the reported reduced reactivity of acrylamides towards radicals, we managed to obtain the alkylated phosphinic tripeptide in high yield. Okay, so in the next step, we tested whether this radical alkylation protocol could work in more sterically hindered scaffolds prepared by the allelic substitution protocol I showed you before, increasing even more the chemical diversity and the possibilities for introduction of conformational constraint. But most importantly, we were interested to enhance the stereoselectivity of this conversion. So after some optimization, we observed that an andamanide group in this position can lead to high distereoselectivities during the addition of isopropyl radicals. And in addition, the triethylborane protocol worked very well when aryl groups are positioned here. But with alkyl groups at the same position, we observed that the best results are obtained with a sodium cyanoborohydride protocol, leading in all cases to diastereoisomeric ratios higher than 95:5. Okay, so moving now to the diversification of this position of phosphinic peptides, the so-called P1 position. Previous reports have demonstrated that phosphinic acids can react with in situ formed imines towards aminophosphinic acids. However, the method is limited by the harsh acidic conditions that are required, which makes it incompatible with acid-sensitive groups. And to address this problem, to address this issue, we thought that maybe we could increase the reactivity of phosphorus nucleophiles by shifting this tautomerization equilibrium of phosphinic acids towards this tervalent species. And we wonder if it would be possible to do that by converting acids to anhydrides. Calculations showed that the tautomerization of either mixed or symmetric anhydrides was indeed less endothermic than that of free phosphinic acids. However, what was really striking is that there was a much bigger improvement when these cyclic anhydrides were employed. These species could probably be formed by the cyclization of the parent diacids that you see here, using dehydrating agent like a carbodiamide and could react with imines under acid catalysis to afford the desired final compounds. If successful, this reaction would be the first example of formation of a PC bond using a carbodiamide, and the first example that the carbodiamide activates a nucleophile instead of an electrophile. So we explored this possibility, and indeed, we found that cyclization with DIC was possible. In fact, it was rapid, and that these cyclic species can react with Boc aminals, which in fact are synthetic equivalents of Boc amines introduced by Maruoka in 2015, using BF3 as a catalyst. Noticed here the two peaks corresponding to these cyclic compounds, and these two peaks are attributed to the chirality at the phosphorus center, and see what happens when a similar phosphinic acid that cannot cyclize happens. This is because the symmetric anhydride is formed, which is far less reactive than the cyclic anhydride, and leads to very small conversions after 24 hours. So this verifies our initial hypothesis. As you can see here, the scope of the reaction with regard to the aminal is very broad, tolerating aryl, alkyl, alkenyl, and alkenyl side chains, as well as functional groups. And in addition, a large variety of substituents at the phosphinic part, at the part of the phosphinic acid was examined, leading in all cases to high yields and reaction times ranging from 1 hour to 24 hours in the case of this very hindered product. Now, concerning the reaction mechanism, Professor Voyagis from the University of Tennessee helped us here with DFT calculations to propose the following scenario, which involves an ion pair swapping between the anionic parts of ion pair A, which is produced after the unfavorable dissociation of the starting Boc aminal, and ion pair B, which positions the phosphorus nucleophile in close proximity to the iminum species. This exchange over here was found to be highly exothermic and favoring the ion pair B, which rapidly collapses to the final products by forming a stable phosphorus carbon bond which cannot dissociate. Now, let's see another synthetic problem that we recently worked on concerning the development of a reliable and scalable synthetic protocol for the stereochemical control of this position over here, the P1 prime position of phosphinic peptides, that would not require chiral auxiliaries or chiral catalysts or predefined chirality at phosphorus atom, as it happens in most reported methods in the literature, which have found very limited use. So we noticed that there are a few examples in the literature where modest DR values can be achieved in a standard phosphamidyl reaction between chiral aminophosphinic acids and acrylates under silylating conditions. So we explored how we could maximize this inherent stereoselectivity of this reaction and develop a protocol that would offer operational simplicity, broad substrate scope, scalability, and if successful, no need for chirality at phosphorus center or chiral auxiliaries or catalysts. In particular, the idea was to establish a 4-point communication in these intermediate TMS enolates between the P1 position of this structure, which is the carrier of stereochemical conformation. This site of protonation, where this information must be transferred, this stereogenic phosphorus and atom and the ester group that could probably act as a critical factor for the attenuation of this stereoselectivity. So this is probably too much to fit in a single reaction. However, we were delighted to see that after screening of 30 different ester groups, we got a good stereoselectivity by using this inexpensive benzyl group or DPM group in this reaction. As you can see, incorporation of the DPM group in Michael acceptors led to high DR values up to 30 to 1 in these cases. And in addition, the reaction also works for a wide variety of substituents on the electrophilic part, reaching in several cases diastereomeric ratios higher than 50 to 1. Okay, so we were curious to see how this reaction worked to provide a mechanistic explanation for the observed stereoselectivity. And this is why we monitored the reaction by phosphorus NMR. And what drew our attention was the generation of a single peak at the products region over here, which was found to be the protonated product as a single isomer, which means that there is a stereoselection when this phosphinic ester is generated at the level of a parent intermediate enolate. So what we propose as a mechanism in this reaction is that the reaction initially leads to these equilibrating transient oxaphospholene adducts, which collapse to TMS enolates. And during this transformation, the stereochemistry at the phosphorus center is controlled through a process which is strongly influenced by the presence of a DPM group, leading to stereochemical enrichment of phosphorus center, which in turn determines the fate of the protonation step. DFT calculations showed that the intermediate possessing the S stereochemistry at phosphorus atom is significantly more stable than the R isomer. And according to this calculated structure, we could explain the generated stereochemistry by forcing protonation by the bulky proton donor to occur from the most accessible outer phase and produce the observed stereochemical outcome. Well, I don't know if I have more time to go through this slide.
Well, actually, we are a bit late in time, so if you...
Okay, so maybe I will skip this slide and go directly to probably the most important one, which first I hope that I gave you a small sample of what we are doing in our group and convince some of you about the potential of organophosphorus peptidomimetics and their challenging synthetic chemistry. Of course, nothing would be possible without the efforts of all current and past members of our group that have been doing an excellent job all these years in all the projects that you have seen. I'm really grateful to them for the inspiring interactions that we are having. Their motivation is the fuel for keep us moving forward. And of course, the funding sources and all of you for your kind attention.
Thank you, Dimitris, for beautiful talk, very careful work. It's open for discussion, and I see the first question from Alexandros. Please go ahead.
Oh, thank you. So the only thing that I want to say is to congratulate Dimitris, because it is really impressive to see how late-stage functionalization in this complex setting is done. I think it's amazing how you succeed to do this, Dimitris. Congratulations again.
Thank you, Alex. Probably there are more to come. Probably in the next.
I'm indeed also impressed by the super high diastereoselectivity in this final part, where, I mean, we all know, of course, the phase selective protonation and so on, but what you normally see in literature is 5 to 1, 10 to 1, but you go to even 20 or 30 to 1.
Up to 50 to 1, yes.
Yeah, that's super.
Yeah. Well, it has to do with the system, with this specific structure that probably combines many parameters in order to have this final result. So it's not something that can be generalized, but works very well in this context.
I see. Yeah, and as a, let's say, a protecting group for the phosphinic acid, you often choose the adamantyl protecting group. Is that your favorite choice anyway, or does it have special properties, or is it just because it's big?
Well, actually, adamantyl group can be removed under acidic conditions from the phosphinic acid and from the phosphinic moiety. And this is something that we need when we do solid phase peptide synthesis during the final deprotection. So historically, it's a protecting group that we prefer to that direction. And in some cases, it offers some additional advantages, as we saw in the case of this diastereoselectivity directing effect in the radical addition reaction.
Okay. Yeah, thank you. And I was about to say that Kim Lambres has the honor of posing the first question in the Q&A session, but she also gave the answer in the second message. So that question is apparently obsolete.
I was wondering if the participants were indeed attending.
So your lecture was very clear.
I will rephrase the origin of stereocontrol in the Phosphan-Michael addition. The origin of stereocontrol, yes. So the origin of stereocontrol, the only stereochemical information we have to the reactants of this reaction is this. Is the stereochemistry at this position, the P1 position. So the stereochemical information from this position somehow is transferred to the protonation side. But this transfer is not direct, it's indirect. This stereochemical information here first determines the stereochemistry of the phosphorus center, and this effect is maximized by the DPM group. And then the protonation is directed by the stereochemistry of the phosphorus center. So it's an indirect effect. But the source of the stereocontrol is the stereochemistry that we have in this position, the P1 position. I don't know if I managed to answer the question.
I think so.
Okay.
We just assume that it's the case. Thank you very much. Thanks once again for our presentation. And then we go to the next and final presentation by Konstantinos Neogritas from Crete. Sorry, yeah, it says here Thessaloniki.
No, it's Crete.
Yeah, I thought so, Adinos.
I'm coming from Thessaloniki, but I'm born in Crete. Okay, let's share my screen since it's one of the most stressful things for this meeting.
That's always the first training you get here.
Yeah. I think.
Now we see your present. Yeah, now.
Yeah. Now
you passed the bar, Dinos. My compliments. Yeah.
Yep. This is the benefits of being the last one. Okay. Thanks everybody for this invitation. I will try to be brief because I know you are tired and maybe you are hungry. And so, twist, turn, react, controlling anthropisomerism through MCR chemistry. This is my talk. I will briefly mention, let me hide some stuff here, hide video panel. Okay, I will go through some recent developments of our group, and I will focus on anthropisomerism that we are entering currently. Now, I will start with a reverse order than the previous speakers. A big thanks to my group, which are a very dedicated, talented group of graduate and undergraduate students. And without them, nothing, and I mean nothing, would be possible of all of this nice chemistry that you will see. So, a fundamental question why are you synthesizing molecules? Since we are all a bit of synthetic organic chemists here. And of course, there are a lot of answers to this question. But the thing that I personally believe it's what is also described by the mantra of Association of Greek Chemists, and this is an exhibition of Association of Greek Chemists, chemistry for a better world. So I believe that we are synthesizing in order to make a better world. And just a random choice of my favorites, fertilizers, penicillin, with the Nobel Prize date that I put there, the pill, polymers, lithium-ion batteries, is some of the developments in chemistry that really help the world. Of course, there are plenty of more, but I believe synthesis is how to serve the society. And I'm really glad that Professor Georgiadis was a bit prior to me. Another thing, structure means properties. And if you are controlling the structure, and as a chemist, as an organic chemist, we really know this, you control the properties. Now, our gears in the Southern Chemistry Department, University of Crete, I have a strong focus, as you saw from introduction of Professor Likakis, is multi-component reactions. And I have, let's say, two gears. One is drug discovery. We are starting from design, docking, cheminformatics, library synthesis, structural activity relationship studies. And the second one is new modalities, synthetic methodology of new functional groups, unprecedented scaffolds, and we really like difficult to make molecules, microcycles, covalent inhibitors, 3D molecules, and much more. Now, what I'm doing, what we are doing the last 4 years, I'm currently 5 years here, 4 years I'm active as a researcher. We synthesize some tetrazole indoles, privileged scaffolds, difficult to access otherwise. With a similar strategy, we synthesize indole 2 amides. The 3D structures that you see here are actually single crystal structures because we are, as you will see later, we were much fond of conformations. Then we synthesized artificial microcycles. We did microcycles difficult to access with 9, 10, 11, 12, and even more ring sizes. We even were able to make CO2 trapping, giving rise to these carbon mates, again, difficult to access ones. Continuing with 7-member rings, heterocycles, benzodioxyquinones as gamma secretase inhibitors, the benzothiazepines, having this nice butterfly type of conformation with fused heterocycles. And some latest developments that we did, novel multi-component reactions, exploiting interrupted versions of these, novel chemotypes leading to peptidomimetics, C1 chemistry, addition of only one carbon giving rise to heterocycles, fused flat rings based with indoles, thiophens, or quinolines. And we also doing a lot of drug discovery. This is one of my first works here. We synthesized and we studied some new local anesthetics. We did some aminoamide type of anesthetics, both old with a new synthetic improved way in water with at room temperature, and new ones. And we tested for the spontaneous activity in hippocampal brain slices. We also described a novel synthesis of ranolazine, the API of ranolazine. I think 2 days ago, we published this work. We were able to evolve fluorescein, a common imaging tool, to a potent theranostic tool, combining both the imaging properties of fluorescein and therapeutic properties as well. Unpublished work we designed and to synthesize the library of covalent inhibitors. This is just one example, thiophene based with a covalent warheads here, and this is the crystal structure of this. And also quite a recent work of us, which is under revision currently. And as Professor Charlie also mentioned about products, we are also interested about the molecular glues, which is a little bit similar, but not the same. For the people that don't know, and for our students, basically are monovalent therapeutics that enhancing the interactions of already known interactions of a protein-protein interaction, or they're bringing neomorphic ones. So we synthesize the library of more than 50 derivatives. We make an extensive SAR. We got co-crystal structures, and this also led to a more rational synthesis and design and synthesis, of course. Now, the focus of my today's talk is about harnessing conformational drivers into drug design. All the people here implied that structure and conformation is important. From Professor Sokrafos to natural products till Professor Georgiadis, conformations are very important. And of course, I don't have to persuade you, especially for everybody else, about the molecular recognition in biological systems. Beta sheets, alpha helix of peptides and proteins till DNA. And today's drug design tries to incorporate this molecular recognition and study these interactions. And what you have to know to do this, geometries and the approximate affinity contributions of attractive interactions. And a common strategy in drug discovery is basically to rigidify flexible structures. And 95% of this is through cyclization. But if we understand better the conformational chemistry, and as this understanding grows, then we will be able to reduce the number of low-energy conformations accessible to the ligand and basically rigidify without eventually cyclize everything. And the last year, 2 years, we dived into atropisomers and atropisomers, which is already a 100 years phenomenon. This is a snapshot from 1922, the first paper that came back then, describing this special type of enantiomerism. And I will not go through details on this. Basically, we have 4 types of atropisomers: the biaryl, which is basically 2 phenyl groups, the heterobiaryl, which is one phenyl one, and this is a heterocycle, and the most interesting one, the C and D, the non-biaryl CC, and the very interesting, to my opinion, of course, non-biaryl CN. This is more interesting because if you see this, there are quite privileged scaffolds and scaffolds that are used over and over again in drug discovery. Of course, with not randomly because they are bringing a lot of properties. Now, the atropisomers in drug discovery got fired the last 5 years. Basically, the atropisomers can be classified into these 3 categories. We have depending on the barrier of this rotational bond, this is the atroposomeric axis. If this barrier is lower than 20 kcal per mole, then these compounds are classified as class 1. Basically, this is a rapid interconversion. You don't care, they're behaving as achiral compounds. If you go with this barrier more than 30 kcal per mole, this is a class 3. Again, these are obtained as achiral again, as perceived as achiral, because it's really difficult to move around. The interconversion could take centuries or thousands of years, and I'm not exaggerating. And the middle category is the most tedious and the most dangerous one. It's 20 and 30 kcal per mole. And unfortunately, we have on all classes, class 1, class 2, class 3, FDA-approved drugs. The problem in the second category is that at the second point at your body, you could have 2 different atropisomers, meaning 2 different enantiomers. And you all know the thalidomide stories and what brought this to the world. Now, have a look on this class 3. This is a sotorasib. This is a KRAS inhibitor, one of the latest approved drugs on a difficult, otherwise to access molecular target, KRAS, cancer target. And people here took advantage of atropisomers. You can see atropisomers here and here. And basically, they did this on purpose. As I tell my students, every drug, the modern drug and the good drug has to rationally impose all the characteristics on the molecule. Every characteristic on the molecule, every feature on the molecule should play a role. And people here introduce on purpose atropisomers in order to target some encrypted binding sites. And this comes to the next slide. Why is it important to synthesize atropisomers in a more targeted and a more controlled way? We have basically 3 strategies to construct atropisomers. 1, construction of serogenic axis through transitional metal catalyzed cross-coupling most of the times. 2, de novo synthesis of an aromatic ring. 3, factionalization of prochiral or racemic bialyls. And of course, all these 3 bring some issues to the table. First of all, atropostability issues, elevated temperatures, CH activation problems, expressed in transitional metals, inert reaction conditions, and this goes on. But one major issue here is that we have limited structural diversity. So we need to find new ways. And last year we thought, why would we target atropasomers with multiple reactions? Because multiple reactions are a more convergent type of chemistry and can bring a lot of good things to the table. So what MCR bring? We can assemble, in general, complex molecular architectures. 2, we can simultaneously install multiple stereogenic elements, and this is important for atropasomers and controlling them. 3, we can utilize rigid and anisotropic structures by imposing spherical constraints. And basically, this is where all the work starts. We started from analyte. This is a known, as you saw in my previous slides, atropisomer, and we converted to this type of scaffold, which is an MCR scaffold, a tetramer one. Basically, this is the 3D conformation of this. So we can install various substitutions here. We call it arms and selves. This is a planar aromatic system, and we use CH pi and pi interactions. And basically, of course, I will not go into details with this. We have 3 different molecules. We synthesized basically a new high rotational barrier, a new class of high rotational barrier atropasomers. We did more than 40 examples. We play a lot with the substituents here. We studied many interactions between arms and selves. We got numerous single crystal structures, verifying our NMR spectra. We did DFT calculations. And this guy here, Dr. Fragiadakis, now he's in Netherlands, by the way, doing his postdoctoral research, along with some students, introduced to the team and to the group the atropasomers, and this is my sub-atropos group. Now, this published, I think, a week ago. We thought, let's move to this chemistry to another type of chemistry, the GBB. GBB comes from Grebke-Blackmer-Benamé reaction. What is that? Basically, it's a 3-component reaction, which is the amino heterocycle, most of the times aminopyridines, aldehydes, and isocyanides, which gives rise to these flat fused aminopyridine derivatives. And this is a privileged structure already because it's existing in many approved drugs. But here I want you to focus on the conformation of this type of molecules. This is from the CCDC database, and you see a common, a typical conformation of this GBB adducts. You see that the aminopyridine is a flat ring, has a T-shaped conformation with the aldehyde, which is this, and the isocyanide part hovers the plane of the aminopyridine. Keep this in mind. Now, we thought, this is what we published in chemistry. Can we now, with all the knowledge that we had from the CH pi and pi interactions, transfer this knowledge into a new scaffold and make a scaffold hopping from a Ugi tetrazole to a GBB? So going from here to here. And the answer is yes. We did a lot of chemistry here. I will not go into details into that. This is a crystal structure that we got. And now if you remember the crystal structure from a typical GBB, which is something like that, you see the difference. And you see how with installing certain CH and pi interactions, we forced the molecule to have a specific conformation. And this is again a high barrier atropisomer. We did all the DFT calculations, we calculated the rotation energies, and we published this, as I told you, some weeks ago. We discovered a nexus of CH pi and pi interactions, and with Professor Harry Storch from Aristotle University of Thessaloniki, we were able also to calculate the isochemical shielding isosurfaces, how the metal group is shielded from the isosurface of an aromatic ring. And you will tell me, okay, so what? Is this important? Can CH pi interactions lead to a different conformation? And I will go back to a work that is in progress. I told you about the molecular glues that we did. And this is a crystal structure, and I extract this molecule from a co-crystal structure. So this is a real crystal structure derived from a co-crystal structure. This is a warhead, moiety. This is a GBB adduct. This is the aldehyde compound. This is the isocyanide. Have a look at this conformation. And while we're doing the SAR, we had to make a more rigid conformation of this molecule. So we thought, let's get into advantage our previous knowledge on controlling the conformation. So install a CH3 here and CH3 here. And look, the new co-crystal structure got how this changed. So we forced this to get almost parallel conformation. And this is a co-crystal structure that we had. And basically, this helped a lot our SM studies, and we make better molecules with much higher affinity. Now, from now on, and this will be my topic of today's talk, will be everything will be is unpublished. So I will talk you about new things. And we thought, because all this work have to do with high rotational barriers, the previous studies, both UGI, tetrazo, and GBP, if we can have access to unprecedented atropasomers. And our strong focus was to privilege scaffolds. For example, hydantoins, diketopeterazines, as Professor Zographos mentioned, oxazines, pyrimidines, and pyrimidinones. We thought if we can control atropaisomerism in these molecules, this could bring some benefit to drug discovery. And of course, we can have knowledge about interaction geometries and affinity contributions of interactions, and we can extremely do with MCR chemistry, of course, extremely fast structure property relationships. Because structure and conformation means properties. Now, I will refer mostly to this project. We did manage this, and we did some synthesis of hydantoins and diketopeterazines. Before I'm going to this, we did this exploiting a UGI-Juliet free reaction combined with an Azinger reaction. This is a union of molecular reactions. But before I'm going to this, let me tell you what is an UGI-Juliet, because maybe people are not very familiar with this. UGI-Juliet basically is an UGI reaction, but the difference is that the imine here is already preformed. So you are adding isocyanide and the carboxylic acid. It's basically a three-component reaction, and you get this type of aminoamide type of scaffolds and UGI adduct. This is UGI-Juliet. So what we thought? We thought to exploit an Azinger reaction. Azinger is a very old reaction, quite neglected, but we're trying to bring it into trend. Chloroacetaldehyde, a ketone, you can use whatever ketone you like. In the presence of sulfur and ammonia, you got this very nice, quantitatively, aminothiazine. But besides this nice privileged scaffold, you can see the preformed now imine. And now you understand, I think, where I'm getting into. We thought let's do an UGI reaction on this molecule. Using isocyanide and a trichloroacetic acid, I will explain you why trichloroacetic acid at room temperature. In only 30 minutes, we got this molecule, the UGI adduct. Now, we already seeing in NMR a spontaneous cyclization to this molecule. So, optimizing a little bit, using triethylamine, we got this cyclization to hydantoins. Hydantoins are a special type of heterocycle. Of course, there are a lot of drugs based on hydantoins and diketopeterazines, but are quite peptidomimetics, and basically they're controlling the conformation of peptides. They're used a lot in drug discovery. So 30 minutes here, 30 minutes, 30 minutes, we got a final adduct and hydantoin. Again, with the same similar strategy, an UGI reaction with isocyanide and chloroacetic acid this time, giving rise to this UGI adduct. Cyclization, this time it's a little bit more difficult cyclization, sodium hydride, but quite fast, rise to diketopeterazines. Now, these diketopeterazines and hydantoins can be basically, we can construct a library in one a day. And you don't need purification here, either here. And if you scale up, you don't even to purify by column chromatography even here. We just wash it, and you can perfectly clean adducts. And maybe this is an idea for Professor Zographos, if we can use this as a catalyst, this diketopeterazines. You can basically just prepare some of this in 3-gram scale. Scalability is also not a problem. Now, going to the atropaisomerism, you can see with the red, the supposedly stereogenic atropasomeric axis. This is what we did this. Now, this strategy, because this is, I think we hope to publish this. This is a modified Azinger, UGI-Juliet, and cyclization, and we coined this as a MOSI tactics. Now, This is an example of the library that we did. We did much more, but just I want to show you what we observed. Have a look on this one. You see here a stereogenic center. And this, with the highlighted cyan color, you see the supposedly stereogenic axis. Now, have a look on what we saw in the NMR. In NMR, we saw a diasteromeric mixture. This means that we brought to the table a second stereogenic element. And this is the axis, because you already have a stereogenic center. So we were able to see for the first time atropisomers in this type of scaffolds. And of course, on purpose, we substituted in the ortho position. We did quite some work here. In most of the times, you see 1-to-1, but in some cases, like this one, you see a little bit difference of the 1-1, 1-to-0.7, and here with the ester group, 1-to-0.4. Currently, investigation is under work, but we believe some fluorine oxygen or oxygen CH oxygen interactions, or here repulsion between oxygens would influence the population of the different atropisomers. Regarding the ketopeperazines now, again, example of a library that we did. Again, stereogenic center, 10-butyl one, stereogenic axis. Now the difference in diasteroselectivity is different than the hidantoins. Yes, we see 1-to-0.7, and here we see 1-to-0.2, and here we see only 1. So this is atroposelective, depending on the substitution here. Also, I see the comparison between hidantoins and the ketopeperazines with the same substituent. Here we have 1-1, here 1-to-0.2. Again, a small difference, CH2 here, completely changed the landscape. Of course, this work will not be as good as it is without the contribution of an excellent student of mine, Maritina, a master student, and a bachelor student, Faye. Now, I told you in the beginning that we are also like very much C1 chemistry, so we thought, let's try to do something like that. Oxazines referred to a lot of drugs as well, and bioactive compounds. And our attention went to this MCR, aldehyde with a hydroxy group on the ortho position, anilines, isonite, TMSazide, gives rise to this tetrazole reaction, which is a no reaction. We saw this the free hydroxy here, the free amine here, and we thought, why can cyclize this with a C1 chemistry? And with CDI most of the times, we were able to get scaffolds like this, where X is oxygen, sulfur, or CO2. Again, trying to install a stereogenic axis, as I indicated with the red here. We synthesize some molecules with different isonites, and now you can see again the diasteromers, and you can see a high difference in their population, 3-1, 4-1. In some cases, we can see only 1. Maybe in fluorine here, we don't see any, maybe we don't have a stereogenic axis anymore when you're using a smaller group, but again, this is under investigation. This work again was done by an excellent student of mine, Konstantina, master student, and Despina, a bachelor student. So women really in my group taking advantage of all the atropos. We were able to get the crystal structure of them. This is what we got. This is a compound. We got the crystal structure both from our NTS, they are co-crystallized. Just for easier navigation for you, I'm highlighting what I'm referring to. This is a stereogenic center, this is a methyl group, and this is the rotational barrier that I'm referring to, the rotational axis, the troposomeric axis. In both cases, we saw RNTs in one crystal structure, but in every time I saw the same atropisomer. So every time I see the major one, because this is 3-1. DFT calculations, NMR studies are still ongoing. I will not want to reveal it now. Have to be a little bit patience. And then continuing in C1 chemistry, we thought, could we target something like that, pyrimidines and pyrimidinones? The answer is again yes. We used this phenylacetaldehyde, this cyanosinamide, Gewalt component reaction, and again, a multi-component reaction with no isocyanide, we got these aminothiophenes. For the people that are doing cyanosinamide chemistry, this is also a bit difficult to access because now we have an aniline. Most of the times in literature, you will see it with benzylamines, but we resolve this issue. And now we see an amine here, an amine here, and with, again, same conditions, CDI, DPA, we were able to cyclize this in getting scaffolds like that. Again, stereogenic axis with red. Refluxing formamide, you got this. Again, quite easily in two-step procedure. Just as an example of what we did. Konstantina, again, is the lady behind all this. We got different scaffolds, different substituents here. Now you don't see a DR, and I suppose you understand why not, because there is no stereogenic center now. Luckily, we were able to get a crystal structure from this, and luckily, both atropasomers were crystallized. One time, the third butyl group is above the plane of this, and the other one is below. Of course, we ran chiral HPLCs. We saw separation of the two atropoenantiomers, and really happy and glad about that. Concluding, and I hope I was too tiring for you, we propose and we synthesize, demonstrate de novo synthesis of atroposomeric privileged scaffolds. We were able to install multiple stereogenic elements and conformations. The work is still ongoing. Basically, whatever functional group you add, it adds on value and adds on knowledge on these interactions. Single crystal structures, chiral HPLCs, dynamic NMRs, DFT calculations are all ongoing. Thank you very much for your attention. A big thanks to the Association of Greek Chemists and the funding agents that make this work true. And since our president here of EuChemS is a Dutch, I think he will appreciate this painting from Peter Thiers, a Flemish painter in Antwerp, which shows the three fates. Atropos was a fate in ancient mythology, who look at us, and this is time. So time, take home message, atropos, atropisomers, and time is always connected. Thank you very much.
Thank you, Dinos, for the beautiful stereochemistry lecture, actually, more or less, atropisomers and then all the three-dimensional. It's very nice that you end up with Greek mythology, but if for the people that noted the details, they saw that George Vassiliou started with actually with a picture of a labyrinth coming from Crete that must have been the labyrinth of the Minotaurus.
We saw a lot of mythology today. So I saw a chimera from Professor Charlie.
Exactly.
I saw the three muses, I think, from someone.
Oh, you can extend this endlessly with Helios using photochemistry. Yeah.
Yes.
Questions for Dinos? Got already congratulations, and here I have a question from Kim Lambrechts. I will try to answer live, Kim, then you can pose the question yourself. So just try to place the question yourself, otherwise I will read it out. Kim, are you there? No, that seems to fail, then I will just read out the question. So what is the estimated rotational barrier for the DKPs? As they are not quaternary substituted, I'm not sure how easy they interconvert. In other words, is this DR then a result of the reaction pathway or interconversion afterwards? In other words, it's kinetic or thermodynamic, what you see.
Currently, this is still ongoing. I think on Monday, our extensive DFT calculation will end, so we'll have a picture. We're trying to, and now we're also trying to hit up in NMR. And till I will give you a spoiler alert, till 80 degrees, we don't see any difference. I mean, in interconverting. So I think the barrier is still high. Although we are seeing coherence of signals a lot, but still we are not in the barrier of this. Another thing is that we can introduce now smaller substituents, and now you can see again how the barrier will influence it. And I think we see a room temperature barrier if we introduce a fluorine, for example, but it's still ongoing. It's not solid yet. This is really latest developments in my group. So basically, the last month, many of these things is from my last month here. So still ongoing.
I see. Another question is it possible to control the enantiomer selectivity in the synthesis of the atropisomers or use some kind of resolution?
Generally, UGI reaction is really bad to control. So basically, you cannot control under this the stereogenic center. But I think we can control the specific atropisomer there by installing a specific substituent in ortho position and take advantage of the CH pi or the oxygen CH interactions.
Yes. All right.
Resolution, of course, we can do it. We separate it chirally through HPLC, and we are able to resolve this in a chiral HPLCs.
Yeah,
This is already done.
Yeah. Right, I see it's 2 o'clock, so if there are no more questions, then I would like to thank the speakers of today, all a series of brilliant lectures. I enjoyed it very much. I'd like to thank Macquarie for setting up the webinar. That's worked perfectly. And with that, I hope to see you back in September for the next highlighting event, which will then be the Netherlands. So thank you all for joining, and thanks once again for your lectures and participation. Thank you.
Thank you.
Thanks a lot, Andrew.
Thank you very much.
Thanks
a lot. Well done, folks. And on my behalf, I'm not at all surprised to see the strength of organic chemistry in Greece, because I've heard many of you talk around Europe and some in Dublin. And I have to say, it's been a really superb morning. Lots of light in Greece, as they say. It's a balmy 18 degrees Celsius here. So maybe I should start thinking about doing some photochemistry in Dublin. It will only work for about 2 weeks a year. But anyway, again, congratulations to you, Jonas. Superb lineup, and thanks for all of your work in the background as well. Adri, thank you again as president, and another fantastic addition to the Highlighting Organic Chemistry series. So have a good weekend. Thanks very much. Bye.
You too. Thank you. Thanks a lot.
Thanks also. Thanks all the invited speakers. Thank you all. It's my pleasure.
We thank you.